The story of our sun begins not with light, but with darkness. 4.6 billion years ago, in a quiet corner of our galaxy, there existed a vast cloud of gas and dust, drifting silently through the void of space. This cloud, known as a molecular cloud, was cold, dark, and seemingly lifeless. It stretched across light years of space, composed primarily of hydrogen, the simplest and most abundant element in the universe, along with traces of helium and tiny amounts of heavier elements forged in the depths of ancient stars that had come before. For millions of years, this cloud drifted peacefully through space, undisturbed and unchanging. But then something happened. Perhaps a nearby star exploded in a supernova, sending shockwaves rippling through the cosmos. Or maybe another cloud passed close enough for gravity to create a disturbance. Whatever the trigger, it set in motion a chain of events that would ultimately lead to the birth of our sun and everything we know. The shock wave compressed part of the cloud, pushing the gas and dust closer together. And here is where gravity, that patient and persistent force, began its work. As the particles were pushed together, their combined gravitational pull became stronger. This stronger gravity pulled in more material from the surrounding cloud, which made the gravity even stronger still. It was a runaway process, a cosmic feedback loop that would not stop until something spectacular happened. As more and more material fell inward, the cloud began to spin. This rotation was a consequence of the conservation of angular momentum, the same principle that causes a figure skater to spin faster when they pull their arms inward. The spinning cloud flattened into a disk, with most of the material falling toward the center, creating a dense core that grew larger and more massive with each passing millennium. Within this collapsing core, the temperature began to rise. When you compress a gas, it heats up. This is simple physics, observable in something as mundane as a bicycle pump growing warm as you use it. But in the forming sun, this process was occurring on an unimaginable scale, as millions upon millions of tons of hydrogen fell inward under gravity's relentless pull. The pressure at the center grew enormous, and with that pressure came heat. For perhaps 50 million years, the proto-sun continued to collapse and heat up. During this time, it was not yet a true star. It glowed with the heat of gravitational contraction, shining with a dull red light. But it was not yet capable of generating its own energy through the process that would define its existence for billions of years to come. The temperature at the core climbed higher and higher. 1 million degrees, 5 million degrees, 10 million degrees. At these extreme temperatures, matter behaves in ways that seem alien to our everyday experience. The hydrogen atoms were moving so fast, with such tremendous energy, that they began to collide with incredible force. Under normal circumstances, hydrogen nuclei, which are simply protons, cannot merge together. They are both positively charged and, like charges, repel each other through the electromagnetic force. This repulsion, known as the Coulomb barrier, prevents protons from getting close enough to interact through the strong nuclear force. the fundamental force that binds atomic nuclei together. But in the core of the proto-sun, conditions were anything but normal. The temperature had reached approximately 15 million degrees Celsius, or 27 million degrees Fahrenheit. At these temperatures, the protons were moving at tremendous speeds, carrying enough kinetic energy to overcome the electromagnetic repulsion between them. When two protons collided with sufficient energy, quantum mechanics allowed something remarkable to occur through a process called quantum tunneling. The protons could effectively pass through the electromagnetic barrier that should keep them apart. When this happened, the strong nuclear force took over, binding the protons together. But two protons alone are unstable. Almost immediately, one of the protons would transform into a neutron through the weak nuclear force, emitting a positron and a neutrino in the process. The result was a nucleus containing one proton and one neutron, the nucleus of deuterium, also known as heavy hydrogen. This was the moment our sun truly ignited. This was the beginning of nuclear fusion, the process that has powered our star for 4.6 billion years and will continue to do so for billions of years into the future. But the fusion process does not stop with deuterium. The deuterium nucleus quickly collides with another proton, forming helium-3, a light isotope of helium with two protons and one neutron. When two helium-3 nuclei collide, they form helium-4, the common form of helium with two protons and two neutrons, releasing two protons back into the stellar furnace to continue the cycle. This chain of reactions, known as the proton-proton chain, is the primary mechanism by which our sun converts hydrogen into helium. Every second, approximately 600 million tons of hydrogen are fused into helium in the sun's core. This number is so large it becomes almost meaningless. So perhaps it helps to think of it this way in just 1 second. The sun converts more mass into energy than humanity has used in our entire history. And here we encounter one of the most famous equations in all of science, E equals mc squared. Einstein's equation tells us that mass and energy are equivalent to sides of the same coin. When hydrogen fuses into helium, the resulting helium nucleus weighs slightly less than the 4 protons that went into making it. Approximately 0.7% of the mass disappears, but it does not truly disappear. It is converted into energy according to Einstein's equation, because the speed of light, represented by c in the equation, is so enormous. And because it is squared in the equation, even tiny amounts of mass convert into tremendous amounts of energy. Every second, about 4 million tons of the sun's mass is converted into pure energy. This energy emerges in the form of gamma-ray photons, particles of light carrying immense energy. But these photons do not immediately escape the sun and travel to Earth. Instead, they begin an epic journey through the sun's interior. A journey that will take not seconds or minutes, but thousands or even hundreds of thousands of years. the sun's core, where fusion occurs, is incredibly dense. Although it makes up only about 2% of the sun's volume, it contains approximately half of the sun's total mass. The atoms are packed so tightly that the density is about 150 times that of water. In these conditions, a photon cannot travel far before it collides with an atom, is absorbed, and then re-emitted in a random direction. This process repeats countless times. A photon might travel just a fraction of a millimeter before being absorbed and re-emitted. Each time it is re-emitted, it goes off in a completely random direction, like a drunkard stumbling through a crowded room. This random walk means that photons take an extraordinarily long time to travel from the core to the surface. Even though the straight-line distance is only about 700,000 kilometers, as photons work their way outward, they gradually lose energy. The gamma rays produced in the core interact with matter, breaking apart into lower energy photons. By the time the energy reaches the outer layers of the sun, it has been transformed into visible light and other forms of electromagnetic radiation. The journey from core to surface takes the photons through several distinct layers of the sun's interior. Immediately surrounding the core is the radiative zone, which extends to about 70% of the sun's radius. In this region, energy moves outward primarily through radiation. The process we have described, where photons are repeatedly absorbed and re-emitted, beyond the radiative zone lies the convective zone, where the mechanism of energy transport changes dramatically. Here, the plasma is cool enough and dense enough that radiation becomes inefficient. Instead, energy is carried by convection. The same process that causes water to circulate in a boiling pot or air to rise on a hot day. Hot plasma rises from the bottom of the convective zone toward the surface, carrying energy with it. When it reaches the surface, it radiates energy into space, cools down, and then sinks back down to be heated again. This creates vast circulation patterns, with hot plasma rising and cool plasma descending in enormous convection cells. Finally, after its epic journey through the sun's interior, the energy reaches the photosphere, the visible surface of the sun. This is the layer we see when we look at the sun. Though you should never look directly at the sun, as it can permanently damage your eyes. The photosphere is about 500 kilometers thick and has a temperature of approximately 5,500 degrees Celsius, or about 10,000 degrees Fahrenheit. From the photosphere, light is finally free to travel unimpeded through space. 8 minutes and 20 seconds later, it reaches Earth, having traveled 150 million kilometers across the solar system. The light that warms your face on a sunny day began its existence in a nuclear fusion reaction deep in the sun's core, then spent thousands of years bouncing randomly through the solar interior before finally making the quick sprint from the sun's surface to your skin. But what keeps the sun stable? Why does it not collapse under its own enormous gravity or explode outward from the tremendous energy being generated in its core? The answer lies in a delicate balance, a cosmic equilibrium that has maintained our sun's stability for billions of years. Gravity is constantly trying to compress the sun, pulling all of its mass inward toward the center. The weight of the sun's outer layers presses down on the core with unimaginable force. If this were the only force at play, the sun would collapse in upon itself. But the nuclear fusion reactions in the core produce tremendous heat and pressure. This thermal pressure pushes outward against gravity's inward pull. In a stable star like our Sun, these two forces are almost perfectly balanced. The outward pressure from fusion precisely counteracts the inward pull of gravity. This balance is called hydrostatic equilibrium, and it is what makes the Sun a stable, long-lived star. This equilibrium is self-regulating. If fusion were to speed up for some reason, producing more energy, the core would heat up and expand. This expansion would decrease the density and temperature of the core, which would slow down the fusion reactions. Conversely, if fusion were to slow down, the core would cool slightly and contract. This contraction would increase the density and temperature, speeding up fusion again. The Sun automatically adjusts itself to maintain balance. There is also a second important balance at play, this one involving energy generation and energy loss. The Sun generates energy in its core through fusion and loses energy from its surface by radiating light into space. In a stable star, these two rates are equal. The Sun generates energy at exactly the rate necessary to replace what it radiates away. This is why stars can shine steadily for billions of years. The Sun is not like a fire burning through fuel at a variable rate. It is more like a finely tuned machine, automatically regulating its energy production to maintain a constant output. The fuel for this machine is hydrogen, and the Sun has a lot of it. The Sun's total mass is approximately 2 times 10 to the power of 30 kilograms, or about 330,000 times the mass of Earth. About 73% of this mass is hydrogen, with most of the rest being helium and just under 2% being heavier elements. However, not all of this hydrogen is available for fusion. Only the core is hot enough and dense enough for fusion to occur. The core contains approximately 10% of the Sun's total mass, which means the Sun has a fuel supply of about 10% of 73% of its total mass available for fusion. Even so, this represents an enormous amount of fuel. The Sun has been fusing hydrogen into helium for approximately 4.6 billion years, and it has used up about half of the hydrogen in its core during this time. It is currently in a phase of stellar evolution called the main sequence, which is the long, stable phase where stars spend most of their lives. Our Sun will remain on the main sequence for approximately another 5 billion years before it exhausts the hydrogen in its core. What happens then is a story for another time. But we can say briefly that the Sun will not simply run out of fuel and go dark. Instead, it will enter new phases of evolution, becoming a red giant star before eventually shedding its outer layers and leaving behind a dense core called a white dwarf. But these events lie billions of years in the future. For now and for the foreseeable future of humanity, the sun will continue to shine steadily, providing the light and warmth that make life on Earth possible. It is worth reflecting on the remarkable chain of circumstances that led to our existence. The sun formed from a cloud of gas that contained elements forged in earlier generations of stars. These ancient stars lived, died, and scattered their enriched material into space, providing the raw materials not just for the sun, but for the planets that formed around it, including Earth. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of these elements were created in stars that died before our sun was born. The sun itself, through its steady fusion of hydrogen into helium, provides the energy that drives weather patterns, ocean currents, and ultimately all life on Earth. Plants capture sunlight through photosynthesis, converting solar energy into chemical energy. Animals eat plants or eat other animals that ate plants, creating a web of life that ultimately traces back to the nuclear fusion reactions occurring in the sun's core. Every breath you take, every movement you make is powered by sunlight, either directly or indirectly. The gasoline that powers cars is derived from ancient plants that captured sunlight millions of years ago. The electricity that lights our homes often comes from burning fossil fuels, which again represent stored sunlight from the distant past, or from renewable sources like solar and wind, which are driven by the sun's energy. In this sense, we are all children of the sun, and the sun itself is a child of the universe, born from the ashes of earlier stars in an ongoing cycle of stellar birth, life and death that has continued for billions of years and will continue for billions more. The story of how the sun was born and what keeps it burning is ultimately a story about the fundamental forces and processes that govern our universe. It is a story about gravity, which gathers matter together. It is a story about nuclear fusion, which powers stars and creates the elements. It is a story about balance and equilibrium, about systems that regulate themselves. And it is a story that connects us through countless generations of stars to the very beginning of the cosmos itself. The sun, that brilliant sphere of light that dominates our daytime sky and makes life possible on Earth, is currently in the prime of its existence. To understand where the sun is in its life story, we need to think of stars as living entities that are born, mature, age, and eventually die, though on timescales that make human lifespans seem like the blink of an eye. Right now, at this very moment, the sun is in what astronomers call the main sequence phase of stellar evolution. This term might sound technical, but it simply refers to the long, stable period of a star's life when it is steadily and reliably fusing hydrogen into helium in its core. The main sequence is not a brief phase or a transitional moment. It is the dominant chapter in a star's biography, the period during which a star spends the vast majority of its existence. To put this in perspective, imagine a human life divided into stages: infancy, childhood, adolescence, adulthood, middle age, and old age. If we were to map a star's life onto this human timeline, the main sequence would be like combining young adulthood, middle age, and a good portion of what we might call the later productive years all into one extended phase. It is the time when a star is mature, stable, and doing exactly what it was born to do. The Sun entered the main sequence approximately 4.6 billion years ago. This date is not arbitrary or guessed at randomly. Scientists have determined the age of the Sun through multiple independent methods, including radiometric dating of the oldest rocks on Earth, analysis of meteorites that formed in the early solar system, and computer models of stellar evolution. All of these methods converge on the same answer. Our Sun is about 4.6 billion years old. For all of those 4.6 billion years, the Sun has been performing the same essential task. In its core, where temperatures reach about 15 million degrees Celsius and pressures are crushing beyond anything we can truly imagine. Hydrogen nuclei are being fused together to form helium. This process, nuclear fusion, releases tremendous amounts of energy according to Einstein's famous equation, E equals mc squared. The energy produced in the core works its way to the surface over thousands of years and then radiates out into space as light and heat. This fusion process is remarkably stable and self-regulating. The Sun maintains a delicate balance between the inward pull of gravity, which tries to compress all of its mass into an ever smaller volume, and the outward pressure from the heat and energy generated by fusion, which pushes back against gravity's relentless squeeze. When these two forces are in equilibrium, the star neither collapses nor explodes. It simply shines steadily, year after year, century after century, for billions of years. The fact that the Sun has maintained this balance for 4.6 billion years is both remarkable and essential for life on Earth. Complex life requires stability. Imagine if the Sun's output varied wildly, becoming much brighter for 1,000,000 years and then much dimmer for the next 1,000,000 years. Planets would freeze and thaw, making the evolution of complex organisms nearly impossible. But the Sun's main sequence stability has provided Earth with a consistent energy source, allowing life to emerge, evolve, and flourish. Now, when we talk about how much fuel the Sun has left, we need to be precise about what we mean by fuel. The Sun is not burning in the chemical sense, like wood in a fireplace or gasoline in an engine. Chemical burning involves electrons being rearranged as atoms form new molecular bonds. Nuclear fusion is something entirely different. It involves the nuclei of atoms being forced together to create new elements, releasing energy in the process. The fuel for the Sun's fusion reactions is hydrogen, the simplest and most abundant element in the universe. The Sun is primarily made of hydrogen. When it first formed from a collapsing cloud of gas and dust, approximately 73% of its mass was hydrogen, about 25% was helium, and the remaining 2% consisted of all the other elements combined, everything from carbon and oxygen to iron and gold. However, not all of this hydrogen is available as fuel. Nuclear fusion only occurs in the core of the Sun, where conditions are extreme enough for hydrogen nuclei to overcome their electromagnetic repulsion and fuse together. The core is incredibly hot and dense, containing about half of the Sun's total mass squeezed into a volume that represents only about 2% of the Sun's total volume. Outside the core, the temperature and pressure drop off and fusion cannot occur. This means that only the hydrogen in the core, roughly 10% of the Sun's total mass, is accessible fuel for fusion. The hydrogen in the outer layers might as well not exist from the perspective of energy generation. It is simply not hot enough or compressed enough to participate in fusion reactions. Over the past 4.6 billion years, the Sun has been steadily converting the hydrogen in its core into helium. Every second, approximately 600 million tons of hydrogen are fused into helium. This sounds like an enormous rate of consumption, and it is. But the Sun is so massive that even at this rate, it has only converted about half of the hydrogen in its core into helium so far. Think about that for a moment. After 4.6 billion years of continuous operation, burning through 600 million tons of hydrogen every single second, the Sun has used up only about half of its core hydrogen fuel. This gives you some sense of just how much fuel the Sun started with and how efficient the fusion process is at extracting energy from matter. So, how much fuel remains? Based on our current understanding of stellar physics and computer models of the Sun's interior, the Sun has approximately another 5 billion years worth of hydrogen fuel left in its core. This estimate comes from detailed calculations that take into account the Sun's mass, its composition, the rate at which it is fusing hydrogen, and how these parameters change slowly over time as the composition of the core evolves. 5 billion years is an almost incomprehensibly long time. To put it in perspective, 5 billion years ago, the Earth itself did not exist. The entire history of Earth, from its formation to the present day, from the first simple cells to the rise of human civilization, has occurred in the same span of time that the Sun has already been shining. And the Sun has an equal amount of time left before it exhausts its core hydrogen. But in 5 billion years, the Earth will be unrecognizable if it even still exists as a habitable world. The continents will have drifted into entirely new configurations. The species alive today will long since have gone extinct or evolved into forms we would not recognize. Human civilization, if it survives, will have had 5 billion years to develop, to spread beyond Earth, perhaps beyond the solar system itself. The universe will be a different place. But here is something important to understand. The Sun will not simply run out of fuel and wink out like a candle being extinguished. The end of the main sequence does not mean the end of the Sun's life or even the end of fusion. It means the end of hydrogen fusion in the core. What happens when the core hydrogen is exhausted? The core will be composed almost entirely of helium at that point, the accumulated ash of billions of years of hydrogen fusion. With no more fusion occurring in the core, there will be nothing to generate the outward pressure needed to balance gravity. Gravity will begin to win the tug of war, and the core will start to contract. As the core contracts, it heats up. This is a consequence of basic physics. When you compress a gas, its temperature rises. The contracting core will become hotter and hotter, and this heat will be transferred to the hydrogen-rich layers immediately surrounding the core. These layers, which were previously too cool for fusion, will heat up enough to begin fusing hydrogen into helium. So the Sun will develop a new structure, a contracting helium core surrounded by a shell where hydrogen is being fused into helium. This shell will actually produce energy more vigorously than the core does now. The increased energy output will cause the outer layers of the Sun to expand dramatically. The Sun will grow larger and larger, swelling to perhaps 100 or even 200 times its current diameter. As it expands, the Sun's outer layers will cool and the Sun's color will shift from yellow to red. At this point, the Sun will have become a red giant star. It will be so large that it may engulf the inner planets, possibly including Earth itself, even if Earth is not directly consumed. The increased heat from the vastly expanded Sun will make our planet utterly uninhabitable, boiling away the oceans and atmosphere. But even the red giant phase is not the end. Eventually, the contracting helium core will become hot enough for a new kind of fusion to begin. At temperatures around 100 million degrees Celsius, helium nuclei can be fused together to form carbon and oxygen. This helium fusion occurs in a complex process called the triple alpha process, where 3 helium nuclei combine to form a single carbon nucleus. For a star with the mass of our Sun, helium fusion will last for a much shorter time than hydrogen fusion, perhaps only a few 100 million years. The Sun will continue to evolve through additional phases, experiencing instabilities and pulsations, gradually shedding its outer layers into space. These expelled layers will form a beautiful planetary nebula, a glowing shell of gas illuminated by the hot core at the center. Eventually, all that will remain of the Sun will be its core, now composed primarily of carbon and oxygen. This core, no longer generating energy through fusion, will slowly cool over trillions of years. It will have become a white dwarf, an incredibly dense object about the size of Earth, but containing about half the mass of the current Sun. A single teaspoon of white dwarf material would weigh several tons on Earth. The white dwarf that was once our Sun will continue to cool and fade, eventually becoming a black dwarf, a cold, dark cinder floating through space. But this final fate lies so far in the future that it is difficult to even conceive of the timescales involved. The universe itself is only about 13.8 billion years old, and it will take trillions of years for white dwarfs to cool to the point where they become black dwarfs. But let us return to the present and to the question at hand. Where is the Sun now in this grand story? It is firmly in the middle of its main sequence phase, the long, stable period of hydrogen fusion. It is approximately halfway through its main sequence lifetime, having already spent 4.6 billion years on the main sequence, and having approximately 5 billion years remaining. In human terms, if the Sun's main sequence life were compressed into a single 80-year human lifespan, the Sun would currently be about 40 years old. It would be in the prime of life, mature and stable, with decades of productive life ahead of it. For those concerned about the fate of Earth and humanity, it is important to emphasize that we have an enormous amount of time before the Sun's evolution poses any direct threat. 5 billion years is so far beyond any practical planning horizon that it borders on the meaningless for human purposes. Humanity has existed in its current form for only about 300,000 years. Civilization has existed for perhaps 10,000 years. Trying to plan for events 5 billion years in the future is like a mayfly, which lives for only a day, trying to contemplate the evolution of mammals over millions of years. However, it is worth noting that long before the Sun becomes a red giant, its gradual brightening during the main sequence will pose challenges for Earth. Stars on the main sequence slowly increase in brightness over time. This happens because as helium accumulates in the core must contract slightly and heat up to maintain the pressure needed to balance gravity. This makes fusion proceed slightly faster, which increases the Sun's energy output. The Sun is currently about 30% brighter than it was when it first entered the main sequence 4.6 billion years ago. Over the next billion years or so, the Sun will continue to brighten gradually. Models suggest that in approximately 1 billion years, the Sun will be bright enough that Earth's oceans will begin to evaporate. The resulting increase in water vapor in the atmosphere will create a runaway greenhouse effect, making Earth uninhabitable for life as we know it. 1 billion years is still an almost unimaginably long time, far longer than the time that has passed since complex multicellular life first appeared on Earth. But it is sobering to realize that Earth's time as a habitable world may be limited not to the 5 billion years until the Sun leaves the main sequence, but to perhaps only 1 billion years or so before the Sun's gradual brightening makes the planet too hot for life. Of course, these timescales assume that humanity does nothing to adapt, or that we remain confined to Earth. A civilization that survives for even a few thousand more years, let alone millions or billions, would likely have technological capabilities that seem like magic to us today. We might find ways to move Earth to a more distant orbit as the Sun brightens, or we might have long since spread to other worlds around other stars, making the eventual fate of the Sun and Earth merely one chapter in a much longer human story. The study of the Sun's current stage and its remaining fuel is not merely an academic exercise. Understanding stellar evolution helps us understand our place in the cosmos and the deep connections between stars and life. The Sun created the conditions that allowed Earth to be habitable. Its stability has allowed life to evolve and complexity to emerge. And the elements that make up our bodies, the oxygen we breathe, the carbon in our DNA, were forged in stars that lived and died before the Sun was born. We are, in a very real sense, made of stardust, and we live under the light of a star that is in the prime of its life. A star that will continue to shine reliably for billions of years to come, long enough for life and intelligence to continue evolving in ways we cannot predict or imagine. The Sun's current stability and its vast remaining fuel supply are gifts, providing a stable foundation for life and civilization. We live in the golden age of our star, when it shines with steady, reliable light, neither too hot nor too cold, providing just the right amount of energy to maintain liquid water on Earth's surface and to power the biosphere. This golden age will continue for billions of years, a span of time that encompasses all possible human futures. The transformation that occurs inside the Sun as it begins to exhaust its hydrogen fuel is one of the most dramatic and fascinating processes in all of stellar evolution. To understand what happens, we need to journey deep into the heart of our star and follow the changes that unfold over hundreds of millions of years as the Sun approaches the end of its main sequence life. Right now, the Sun's core is a seething cauldron of nuclear fusion, where hydrogen is being converted into helium at a rate of about 600 million tons every second. The core occupies only the central 2% or so of the Sun's volume, but it contains approximately half of the Sun's total mass. The conditions there are extreme beyond our everyday experience. Temperatures of about 15 million degrees Celsius and pressures millions of times greater than Earth's atmosphere. In this core, hydrogen nuclei, which are simply protons, are moving at tremendous speeds due to the extreme temperature. When they collide with sufficient energy, they can overcome their electromagnetic repulsion and fuse together through a series of reactions called the proton-proton chain. The end result is that 4 hydrogen nuclei are converted into one helium nucleus, with a small amount of mass being converted into energy according to Einstein's equation E equals mc squared. This process has been occurring steadily for the past 4.6 billion years. But fusion does not happen uniformly throughout the core. It happens most rapidly at the very center, where temperatures and pressures are highest. Moving outward from the absolute center, the temperature and pressure gradually decrease, and the rate of fusion decreases with them. There is a boundary beyond which conditions are simply not extreme enough for fusion to occur at all. As the Sun has aged, the composition of its core has been changing. Helium has been accumulating as the ash of hydrogen fusion. Think of it like a fire that produces ash. In a fireplace, the ash builds up at the bottom while the wood burns above it. In the Sun's core, helium accumulates, But because the Sun is a ball of gas with no solid boundaries, the helium does not simply fall to the bottom. Instead, it concentrates where it is created, at the center of the core, over billions of years. This helium accumulation has been gradual but relentless. The very center of the Sun now has a higher concentration of helium than the outer parts of the core, creating what astronomers call a helium-enriched core. This changing composition has subtle but important effects on how the Sun operates. Helium is denser than hydrogen. As helium accumulates in the core becomes denser and more compact. To maintain the same pressure to balance gravity, the core must become slightly hotter. This increased temperature makes the hydrogen that remains fuse slightly faster. This is why the Sun has been gradually getting brighter over its lifetime. It is about 30% brighter now than when it first began fusing hydrogen 4.6 billion years ago. Now let us fast forward to the future, to a time approximately 5 billion years from now. The Sun has been steadily fusing hydrogen in its core all this time, and the helium content has been growing. The changes have been slow but cumulative. The core has been getting gradually smaller, denser, and hotter to maintain the balance between gravity and pressure. Eventually, a critical threshold is reached. The hydrogen concentration in the core drops to the point where fusion can no longer generate enough energy to support the weight of the overlying layers. This does not happen suddenly. There is no moment when the last hydrogen atom is fused and fusion abruptly stops. Rather, it is a gradual process. The fusion rate in the core begins to decline because there is simply less hydrogen available to fuse. As the energy generation in the core decreases, the outward pressure that has been holding the Sun up against gravity begins to weaken. Gravity, which has been patiently pulling inward for billions of years, begins to gain the upper hand. The core starts to contract. This contraction is absolutely crucial to understanding what happens next. When a gas is compressed, it heats up. This is basic thermodynamics, the same principle that makes a bicycle pump warm when you use it. But in the Sun's core, this heating occurs on a massive scale. As the helium core contracts under gravity, it grows hotter and hotter. Here is where something interesting happens. The core itself is now mostly helium and cannot fuse because helium requires much higher temperatures to fuse than hydrogen does. Helium nuclei have 2 protons each, meaning they have twice the positive charge of hydrogen nuclei. The electromagnetic repulsion between them is therefore much stronger, and it takes temperatures of about 100 million degrees Celsius to overcome this repulsion and initiate helium fusion. The contracting core is getting hotter, but it has not yet reached this critical temperature. However, immediately surrounding the inert helium core is a layer that is still rich in hydrogen. As the core contracts and heats up, this hydrogen-rich shell also heats up, and when it reaches about 15 million degrees Celsius, something remarkable happens. Hydrogen fusion begins in this shell. The Sun now has a completely different structure than it did during its main sequence life. Instead of fusing hydrogen throughout a large core, it is now fusing hydrogen in a thin shell surrounding an inert helium core. This shell is actually quite thin compared to the Sun's overall size, but the fusion occurring there is vigorous. More vigorous, in fact, than fusion ever was in the main sequence core. Why is shell fusion more powerful than core fusion? The answer lies in the temperature. The contracting helium core is hot and getting hotter. The hydrogen shell immediately surrounding it is being heated from below by the hot core and is therefore hotter than the main sequence core ever was, and the rate of fusion is extremely sensitive to temperature. A small increase in temperature produces a large increase in the fusion rate. This vigorous shell fusion produces more energy than the Sun ever generated during its main sequence life. And this is where things start to become dramatic. All this energy flowing outward from the shell has to go somewhere. It begins to push the outer layers of the Sun outward. The Sun's envelope, all the layers outside the fusing shell, begins to expand. At first, this expansion is slow, but it accelerates over time. The Sun grows larger and larger, swelling to many times its current diameter. As it expands, the outer layers move farther from the core and cool down. The surface temperature drops from its current 5,500 degrees Celsius to perhaps 3,000 or 4,000 degrees Celsius. A cooler surface emits light that is redder in color. This is why the Sun, as it expands, changes from yellow to orange to red. It has become a red giant star, vastly larger than it was during its main sequence life, but with a much cooler surface. Let us pause here to appreciate just how extreme this transformation is. The Sun will expand to perhaps 100 or even 200 times its current diameter. If you could watch this process in time-lapse, you would see the Sun growing to engulf the orbit of Mercury, then Venus, and possibly even Earth. The exact extent of the expansion is difficult to predict, precisely because it depends on details of the Sun's mass loss during this phase. But it is clear that the inner solar system will be dramatically transformed to Earth. If it survives without being directly consumed, will be subjected to intense heat from the nearby giant Sun. The oceans will boil away, the atmosphere will be stripped off, the surface will become molten. Any life that still exists on Earth at this point will be utterly destroyed. Earth will become a scorched, lifeless rock, perhaps eventually spiraling into the Sun as tidal interactions cause its orbit to decay. But let us return our attention to what is happening inside the Sun during this red giant phase. The helium core continues to contract and heat up. As it does, the temperature rises steadily, 100,000 degrees, 1 million degrees, 10 million degrees. The core is approaching the temperature needed for helium fusion, but it has not quite reached it yet. Meanwhile, the hydrogen shell continues to burn, adding more helium to the core. The core grows more massive as helium ash from the shell falls onto it. And as it grows more massive, gravity squeezes it even harder, making it contract even more, which makes it even hotter. For a star like the Sun, something unusual happens during this phase. The core becomes what physicists call electron degenerate. In normal matter, the pressure comes from the thermal motion of atoms bouncing around. The hotter something is, the more pressure it exerts. But in the extreme conditions of the Sun's core, matter enters a state where quantum mechanical effects become important. Electrons, which are a type of particle called fermions, obey the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state. In a normal gas, this is not a significant constraint because there are far more available quantum states than there are electrons. But in the extremely dense core of an evolving star, the electrons get packed so tightly together that they start to fill up all the available low-energy quantum states. When this happens, the electrons resist being compressed further, not because they are hot and bouncing around, but because quantum mechanics forbids them from being squeezed into the same quantum state. This creates what is called degeneracy pressure, a pressure that depends on density but not on temperature. This has profound implications. In a normal gas, if you add heat, the gas expands and cools, creating a natural feedback mechanism that stabilizes the gas. In a degenerate gas, adding heat does not cause expansion in the same way. The gas can heat up tremendously without expanding to cool itself down. The Sun's helium core becomes electron degenerate while it is still heating up toward the temperature needed for helium fusion. The temperature climbs higher and higher, 50 million degrees, 70 million degrees, 90 million degrees, and then at approximately 100 million degrees Celsius, helium fusion ignites. In a normal, non-degenerate gas, the ignition of a new fusion process would cause the gas to expand and cool, creating a gentle transition to the new fusion regime. But in the degenerate core of the Sun, something much more violent occurs: the helium flash. When helium fusion begins in the degenerate core, it releases tremendous amounts of energy. Normally, this energy would cause the core to expand and cool, which would slow down the fusion rate. But because the core is degenerate, it does not expand normally. Instead, the energy goes into heating the core even more, and because fusion rates are extremely sensitive to temperature, this heating causes the fusion rate to increase dramatically. The fusion rate increases, which releases more energy, which heats the core more, which increases the fusion rate even further. It is a runaway process, a thermonuclear explosion occurring in the heart of the Sun in a matter of seconds. The energy output of the core can increase to hundreds of billions of times the Sun's current luminosity. This sounds catastrophic, and in a sense it is, but it happens deep inside the Sun, and the enormous mass of the overlying layers dampens and absorbs the explosion. The outer layers of the Sun do not even notice the helium flash. They simply experience a rapid heating and some adjustments in their structure. The helium flash itself lasts only a few seconds or minutes, but it has a crucial effect. It delivers enough energy to the core to lift it out of degeneracy. The core expands, becomes non-regenerate, and settles into a stable state where it is fusing helium into a carbon and oxygen through a process called the triple alpha process. In the triple alpha process, to helium nuclei, also called alpha particles, briefly combine to form a beryllium-8 nucleus. This beryllium-8 is unstable and normally falls apart almost immediately, but in the dense core of the Sun, before it can decay, a third helium nucleus collides with it, forming a stable carbon-12 nucleus. Sometimes an additional helium nucleus is added to the carbon, forming oxygen-16. The Sun now has yet another internal structure. It has a core fusing helium into carbon and oxygen, surrounded by a shell fusing hydrogen into helium, all surrounded by the vast extended envelope of the red giant. This structure is more complex than the simple main sequence structure, and it is less stable. The helium-burning core is smaller and less massive than the hydrogen-burning core of the main sequence Sun. It contains only a small fraction of the Sun's total mass. And because it is small and has limited fuel, helium fusion cannot last nearly as long as hydrogen fusion did, where hydrogen fusion powered the Sun for about 10 billion years total. Helium fusion will last for only about 100 million years, just 1% as long. During this phase, the Sun will remain a red giant, though its exact size and brightness will vary. The outer layers of the Sun may become unstable, pulsating and varying in brightness over time. The Sun may go through periods where it sheds mass into space, blowing off some of its outer envelope in stellar winds. As helium fuses into carbon and oxygen, these heavier elements accumulate in the core, just as helium accumulated during hydrogen fusion. Eventually, the helium in the core runs out, and once again, the core becomes inert. An inert carbon-oxygen core forms at the center, surrounded by a helium-fusing shell, which is itself surrounded by a hydrogen-fusing shell, all within the extended red giant envelope. For more massive stars, the story continues. The carbon-oxygen core would contract and heat up until it became hot enough to fuse carbon into even heavier elements like neon, magnesium, and eventually iron. But the Sun is not massive enough for this to happen. Its core will never reach the temperatures needed to fuse carbon. Instead, the Sun will become increasingly unstable. The outer layers will pulsate more and more dramatically. Strong stellar winds will blow away much of the envelope, shedding mass into space. These ejected layers will form a planetary nebula, a beautiful glowing shell of gas surrounding the remnant core. The core itself, composed of carbon and oxygen, will be left behind as a white dwarf. It will be incredibly dense, packing about half the original mass of the Sun into a sphere about the size of Earth. With no fusion to generate energy, it will simply cool over trillions of years. gradually fading from white to yellow to red to eventually a cold, dark black dwarf. Though the universe is not yet old enough for any white dwarfs to have cooled to this final state, the transformation from main sequence star to red giant to white dwarf is one of the fundamental pathways of stellar evolution. It is the fate that awaits all stars with masses similar to the Sun, from about half the Sun's mass up to about 8 times the Sun's mass. More massive stars meet more violent ends as supernova, while less massive stars evolve more slowly and have not yet had time to evolve off the main sequence in the current age of the universe. What happens inside the Sun as it runs out of hydrogen is ultimately a story of changing balances and shifting equilibria. It is a story of gravity and pressure, of contraction and heating, of new fusion processes igniting to temporarily stave off collapse. It is a story that plays out over hundreds of millions to billions of years, on scales of size and temperature and density that are difficult for human minds to grasp. But it is also our story because we are intimately connected to this process. The Sun gave birth to the solar system and continues to sustain life on Earth when it eventually evolves into a red giant. It will bring an end to the Earth as we know it, and the carbon and oxygen that will make up the white dwarf remnant are the same elements that form the basis of all life on Earth. We are made of the stuff that stars create in their cores, returned to the cosmos when stars die. Understanding what happens inside a star as it exhausts its fuel gives us insight into the cycles of matter and energy that govern the universe. It connects the fate of our own Sun to the fates of billions of other stars throughout the cosmos, all following similar pathways determined by the laws of physics and the initial mass with which they were born. The transformation of the Sun into a red giant will be the most catastrophic event in the history of our solar system. It will reshape the planetary system entirely, destroying some worlds, dramatically altering others, and creating conditions so extreme that they challenge our imagination. To understand the full scope of this transformation, we need to follow the changes that will unfold across billions of years and examine how each part of the solar system will be affected. Let us begin with the timeline. The Sun will not become a red giant overnight or even over millions of years. The transition from main sequence star to red giant will occur gradually over hundreds of millions of years. However, long before the Sun actually swells into a red giant, Earth will already be experiencing dramatic changes due to the Sun's gradual brightening during its late main sequence phase. As we discussed earlier, the Sun is slowly getting brighter as it ages. This brightening is a natural consequence of the changing composition of its core as helium accumulates. The Sun is already about 30% brighter than it was when it first formed 4.6 billion years ago, and this gradual increase will continue. In approximately 1 billion years from now, the Sun will be about 10% brighter than it is today. This might not sound like much, but it will have profound effects on Earth's climate. The additional solar energy will cause Earth's surface temperature to rise. More water will evaporate from the oceans, increasing the amount of water vapor in the atmosphere. Water vapor is a powerful greenhouse gas. As more water enters the atmosphere, it will trap more heat, causing temperatures to rise further, which will cause even more water to evaporate. This is called a runaway greenhouse effect, and it represents a point of no return for Earth's climate. The oceans will begin to boil, not all at once, but gradually the seas will evaporate, sending vast quantities of water vapor into the atmosphere. The atmospheric pressure will increase dramatically as the atmosphere thickens with steam. Temperatures at the surface will soar to hundreds of degrees Celsius. High in the atmosphere, ultraviolet radiation from the sun will break apart water molecules into hydrogen and oxygen. The light hydrogen will escape into space. Lost forever from Earth, over hundreds of millions of years, Earth will lose its oceans entirely, transformed from a blue water world into a dry, scorched planet more like Venus is today. This catastrophic climate change will occur roughly 1 billion years from now, long before the Sun actually becomes a red giant. Any life that still exists on Earth at that time will be extinguished. The complex biosphere that has flourished for billions of years will come to an end. Earth will become sterile, its surface baked dry under an ever-brightening sun. But the story does not end there. The sun will continue to brighten and evolve. Around 5 billion years from now, the sun will exhaust the hydrogen in its core and begin its transition to the red giant phase. The core will contract and hydrogen fusion will ignite in a shell around the inert helium core. The energy from this shell fusion will push the sun's outer layers outward. The sun will begin to swell over a period of perhaps several 100 million years. It will expand from its current diameter of about 1.4 million kilometers to perhaps 150 million kilometers or more. That is roughly the distance from the Sun to Earth's current orbit. As the sun expands, its outer layers will cool, and its color will shift from yellow to orange to deep red. But even though the surface is cooler, the total energy output of the red giant sun will be much greater than it is today, perhaps 1,000 times greater or more. This is because the sun's surface area will be vastly larger, and even though each square meter of surface is cooler and radiates less energy, the total surface area will be so enormous that the total energy output increases dramatically. What will happen to Earth as the sun expands toward it? This is one of the most uncertain questions in planetary science, and the answer depends on several factors that are difficult to predict precisely. First, we must consider that the sun will lose mass during its red giant phase. Strong stellar winds will blow material away from the sun's outer layers, carrying it off into space. The sun might lose 20 to 30% or more of its total mass during this phase. As the sun loses mass, its gravitational pull on the planets weakens. This will cause the planet's orbits to expand outward. If Earth's orbit expands fast enough as the Sun loses mass, it might move outward quickly enough to avoid being engulfed by the swelling Sun. Some calculations suggest that Earth might survive, ending up in a more distant orbit around the red giant Sun. Other calculations suggest that Earth will not move outward fast enough and will be consumed. There is also another effect to consider: tidal interactions. As the Sun expands and its outer layers approach Earth, there will be tidal forces between the Sun and Earth. These forces will cause Earth's orbit to decay, making it spiral slowly inward toward the Sun. This effect works against the outward expansion of the orbit due to mass loss. The balance between these two effects, orbital expansion due to solar mass loss and orbital decay due to tidal forces, is extremely difficult to calculate precisely. Different models give different results. Some suggest Earth will survive, ending up in an orbit at perhaps 1.2 or 1.5 times its current distance from the Sun. Others suggest Earth will spiral inward and be consumed by the expanding Sun. Even if Earth avoids being directly consumed, its fate will be grim. The intense heat from the nearby red giant will raise surface temperatures to thousands of degrees. Any remaining atmosphere will be blown away by the intense solar wind. The surface will melt, becoming an ocean of molten rock. Earth will become a lifeless, possibly molten ball of rock, either orbiting within the outer layers of the red giant Sun or just barely outside them. The Moon, Earth's companion for over 4 billion years, will share whatever fate befalls Earth. If Earth survives outside the Sun, the Moon will continue to orbit Earth, though it too will be scorched and transformed beyond recognition. Now, let us consider the other planets and how they will fare during the Sun's red giant phase. Mercury, the closest planet to the Sun, will certainly be consumed. There is no question about this. As the Sun expands, Mercury will be one of the first victims. It will spiral inward through the Sun's outer layers, experiencing tremendous drag as it plows through the tenuous but still substantial gas. The friction will heat Mercury to the point where it vaporizes its atoms, mixing with the solar material. Mercury will simply cease to exist as a distinct object. Venus, the second planet, will almost certainly meet the same fate as Mercury. Even in the most optimistic scenarios where the Sun's expansion is limited, Venus is so close to the Sun that it will likely be engulfed. Like Mercury, it will spiral inward, be torn apart by tidal forces, and eventually vaporize in the intense heat of the Sun's outer envelope. Mars, the fourth planet from the Sun, has a much better chance of survival. It orbits at about 1.5 times Earth's distance from the Sun, and most models suggest the Sun will not expand quite far enough to reach Mars. As the Sun loses mass, Mars' orbit will expand outward, carrying it to safety. But survival does not mean Mars will be unchanged. The intense radiation from the red giant Sun will have dramatic effects even at Mars' distance. The surface temperature will rise dramatically. Any ice in the Martian polar caps or buried in the soil will melt and then evaporate. For a time, Mars might actually become warmer and more hospitable than it has been for billions of years. However, this warmth will come at a cost. The thin Martian atmosphere will be heated and likely blown away by the intense solar wind from the red giant. Whatever water is released from the ice will break apart in the upper atmosphere and escape into space. Mars will be baked dry, left as a barren, airless rock orbiting a bloated red sun. Beyond Mars lie the gas giants Jupiter, Saturn, Uranus, and Neptune. These massive worlds will be far enough from the Sun to avoid being engulfed, and their orbits will expand outward as the Sun loses mass. But they too will experience dramatic changes. The intense radiation from the red giant Sun will heat the outer atmospheres of these planets. The increased heat will cause their atmospheres to expand and become more active. Jupiter and Saturn might develop much more vigorous weather systems, with faster winds and larger storms than we see today. The moons of these giant planets will experience the most interesting changes. Many of these moons are icy worlds covered in frozen water or other ices. As the Sun becomes a red giant and its energy output increases, these icy moons will warm up. Europa, one of Jupiter's moons, currently has a thick ice shell covering what is believed to be a subsurface ocean of liquid water. As the Sun brightens, this ice will begin to melt. The surface might transform from a frozen wasteland to a world with liquid water on its surface. Similar changes might occur on other icy moons, like Enceladus at Saturn or Titan, which currently has lakes of liquid methane and ethane, but might warm enough for water to exist in liquid form for a brief period in cosmic history. Some of these moons might become habitable oases in a solar system, where the inner planets have been destroyed or rendered completely lifeless. If life still exists anywhere in the solar system at this time, these moons might be the only refuges. Of course, this is speculation for a time billions of years in the future, and whether any life, especially intelligent life, still exists in the solar system at that time is unknown. The asteroid belt, located between Mars and Jupiter, will also be affected. The increased solar radiation will heat the asteroids, causing any volatile materials like water ice or frozen carbon dioxide to sublimate into space. The asteroids will become drier and more depleted in these lighter elements. Some asteroids might fragment as internal ices vaporize and create pressure. Beyond Neptune lies the Kuiper Belt and the distant Oort cloud. Regions populated by countless icy bodies, including dwarf planets like Pluto. These distant objects will barely notice the Sun's transformation. They are so far from the Sun that even a red giant will appear as little more than a very bright star. They will warm up slightly, but the effect will be minimal at such extreme distances. However, the increased solar wind from the red giant might affect even these distant objects. The wind will carry charged particles and magnetic fields far out into the solar system, potentially affecting the surfaces of these icy bodies and stripping away some of their thin atmospheres if they have any. One of the most dramatic effects of the Sun's red giant phase will be the alteration of the solar system's overall structure. The Sun's mass loss will cause all the planets to move to more distant orbits. The entire solar system will expand, with each planet ending up farther from the Sun than it started. This will change the orbital periods of the planets, alter their gravitational interactions with each other, and potentially destabilize some orbits. There is even a possibility, though it is difficult to calculate precisely, that some planets might be ejected from the solar system entirely during this period of upheaval. Gravitational interactions between planets might be amplified as their orbits shift, and in some scenarios, one or more planets could be flung out into interstellar space. The comets, those icy wanderers that occasionally visit the inner solar system, will also be affected. Many comets originate from the Oort cloud, and the changing solar wind and radiation environment might perturb their orbits, sending some on new trajectories. However, with the inner solar system becoming inhospitable, any comets that venture close to the red giant sun will be completely destroyed, vaporized long before they reach planet. It is important to emphasize that all of these changes will unfold over immense periods of time. The transition from main sequence star to red giant will take hundreds of millions of years. The red giant phase itself will last for hundreds of millions of years more. These are timescales so long that continents on Earth drift thousands of kilometers, mountain ranges rise and erode away entirely, and species evolve, flourish, and go extinct countless times. For any civilization that might exist in the solar system during this time, these changes would not happen overnight. There would be millions of years of warning as the sun gradually brightened and expanded. A sufficiently advanced civilization would have ample time to adapt, to move to more distant locations, to build habitats on the moons of the outer planets, or to leave the solar system entirely for other stars. The ultimate fate of Earth and the solar system during the sun's red giant phase is a reminder of the impermanence of all things. The Earth, which has existed for 4.6 billion years and has been home to life for most of that time, will not last forever. The solar system that formed from a collapsing cloud of gas and dust will be fundamentally transformed when the sun evolves. After the red giant phase ends, the sun will shed its outer layers, creating a planetary nebula. The beautiful glowing shells of gas will expand into space, enriching the interstellar medium with heavy elements created in the sun's core. At the center will remain the sun's core, now a white dwarf composed primarily of carbon and oxygen. This white dwarf will be incredibly hot at first, with surface temperatures of perhaps 100,000 degrees Celsius or more. It will be small, about the size of Earth, but incredibly dense. A teaspoon of white dwarf material would weigh several tons. With no fusion to generate energy, the white dwarf will slowly cool over trillions of years, fading from brilliant white to yellow to red to eventually becoming a cold, dark cinder. Any planets that survive the red giant phase will continue to orbit this white dwarf remnant. They will be frozen, dark worlds, receiving almost no heat from the faint white dwarf. The solar system will become a cold, dead place, a graveyard of worlds orbiting the corpse of their star. But even in death, the sun will contribute to the cosmos. The elements created in its core, the carbon and oxygen that make up the white dwarf, are the building blocks of life. The gas shed during the planetary nebula phase will eventually mix with other material in the galaxy, perhaps someday becoming part of a new generation of stars and planets. In this way, the matter that once made up the Sun and its planets will be recycled, continuing the cosmic cycle of birth, death, and rebirth that has been ongoing since the first stars lit up in the early universe. The destruction that the red giant sun will bring to the inner solar system is absolute and final. But it is also natural and inevitable, part of the life cycle of stars. Every star that is similar to the Sun will go through this same process. Every planetary system around such stars will face a similar fate. It is simply the way the universe works. For us living in the present day with the Sun in the prime of its life, these events lie so far in the future that they have no practical impact on our lives or our civilization, but they serve as a powerful reminder of our cosmic context. We live on a small planet, orbiting an ordinary star, in a universe governed by physical laws that operate on timescales of billions of years. Our existence is temporary, a brief moment in cosmic history, but it is also precious and remarkable, a flowering of complexity and consciousness in a universe that will eventually wind down into cold and darkness. Understanding the fate that awaits our Sun and our solar system helps us appreciate the extraordinary gift of our present moment, when Earth is alive, when the Sun shines steadily, and when we have the opportunity, our place in the vast cosmos. The question of whether Earth will survive the Sun's red giant phase is one of the most fascinating and debated topics in planetary science. The answer is far from certain, and different scientific models produce different predictions. To understand why this question is so difficult to answer definitively, we need to examine all the competing forces and factors that will determine Earth's fate as the Sun swells too many times its current size. Let us start with what we know for certain. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin its transformation into a red giant star. As the core contracts and hydrogen begins fusing in a shell around it, the Sun's outer layers will expand dramatically. The Sun will grow from its current diameter of about 1.4 million kilometers to somewhere between 100 million and 300 million kilometers in diameter. This range of possible final sizes is itself part of the uncertainty. The exact size the Sun will reach depends on complex physics involving the Sun's mass loss rate, the efficiency of energy transport in its outer layers, and other factors that are difficult to model precisely. But even taking the conservative estimate of 100 million kilometers, this would place the Sun's surface at approximately 2/3 of Earth's current orbital distance. Earth currently orbits at an average distance of about 150 million kilometers from the Sun. If the Sun expands to 100 million kilometers in radius, its surface would reach 2/3 of the way to Earth's orbit. If the Sun expands to 200 million kilometers or more, it would easily engulf Earth's current position. But here is the crucial point. Earth's orbit will not remain at its current distance. Several processes will cause Earth's orbit to change during the Sun's red giant phase, and these changes might save Earth from being consumed, or they might seal its doom. The outcome depends on which effects dominate. The first major effect to consider is solar mass loss. As the Sun becomes a red giant, it will lose a significant fraction of its mass through stellar winds. These winds are streams of charged particles and gas that flow outward from the Sun's surface, carrying material away into space. During the main sequence, the Sun's solar wind is relatively gentle, causing the Sun to lose only a tiny amount of mass. But during the red giant phase, mass loss becomes much more dramatic. Estimates suggest the Sun might lose anywhere from 20 to 40% of its total mass during its red giant phase. Some models predict even greater mass loss. This lost mass will be blown away into space, eventually dispersing into the interstellar medium and perhaps someday becoming part of new stars and planets. When the Sun loses mass, its gravitational pull on the planets weakens. This causes the planet's orbits to expand outward. This is a consequence of orbital mechanics. The size of a planet's orbit depends on both the planet's orbital speed and the mass of the Sun. If the Sun's mass decreases while the planet's orbital speed remains roughly constant, the orbit must expand to a larger radius to maintain stability. The mathematics of this effect are well understood. If the Sun loses, say, 30% of its mass, Earth's orbital radius will increase by approximately 40%. Instead of orbiting at 150 million kilometers, Earth would orbit at about 210 million kilometers. This outward migration might carry Earth beyond the reach of the expanding Sun. However, there is a second major effect working in the opposite direction: tidal forces and orbital decay. As the Sun expands, its outer layers will become increasingly diffuse and extended. If these outer layers reach close to Earth's orbit, Earth will begin to experience drag as it plows through this tenuous material. Even though the Sun's outer envelope is extremely thin by terrestrial standards, it is not a perfect vacuum. Earth moving through this material at its orbital speed of about 30 kilometers per second will collide with countless atoms and ions. Each collision removes a tiny amount of energy from Earth's orbit. Over time, this drag will cause Earth's orbit to decay, meaning Earth will spiral slowly inward toward the Sun. Additionally, there are tidal effects to consider. The Sun's gravitational pull creates tidal bulges on Earth, just as the Moon's gravity creates ocean tides. As the Sun expands and its rotation rate changes, the interaction between these tidal bulges and the Sun's gravity can transfer angular momentum between Earth's orbit and the Sun's rotation. The details are complex, but the net effect is generally to cause Earth's orbit to decay. The critical question is, which effect wins? Does Earth's orbit expand outward fast enough due to solar mass loss to escape the expanding Sun? Or does orbital decay from drag and tidal effects cause Earth to spiral inward faster than it can escape? The answer depends on the precise details of the Sun's evolution, and this is where different scientific models disagree. The rate at which the Sun loses mass, the exact size to which it expands, the density of its outer envelope, the timescale over which the expansion occurs. All of these factors influence the final outcome, and all of them have uncertainties. Some models, particularly older ones from several decades ago, predicted that Earth would survive. These models suggested that solar mass loss would be substantial enough and occur early enough in the red giant phase that Earth's orbit would expand beyond the reach of the Sun's maximum size. In these scenarios, Earth would end up in a more distant orbit, perhaps at 1.5 or 2 times its current distance, safely beyond the Sun's surface. More recent models, using improved understanding of stellar evolution and more sophisticated computer simulations, have painted a more pessimistic picture. Many of these newer studies suggest that Earth will not escape the combination of the Sun's expansion, the slower-than-hoped rate of orbital expansion, and the drag effects of moving through the Sun's outer envelope conspire to doom Earth. In these models, Earth does initially move outward as the Sun loses mass, but the Sun expands faster than Earth can retreat. The Sun's tenuous outer layers reach Earth's orbit, and Earth begins to experience atmospheric drag. This drag causes Earth to spiral inward, even as the Sun continues to expand outward. Eventually, Earth crosses into denser regions of the Sun's envelope. The drag increases dramatically, and Earth plunges rapidly inward, ultimately being consumed. One particularly detailed study published in the early 2000s used sophisticated models of the Sun's evolution and calculated Earth's orbital dynamics throughout the red giant phase. This study concluded that Earth would likely be engulfed, vaporized in the Sun's outer layers approximately 7.5 billion years from now, about 2 billion years after the Sun first begins its red giant expansion. However, even this conclusion comes with caveats and uncertainties. The study's authors acknowledged that their models involved assumptions that might not be perfectly accurate. Small changes in parameters, like the efficiency of mass loss or the structure of the Sun's envelope, could change the outcome. Another source of uncertainty comes from the fact that we have never observed this process directly. We cannot watch a star like the Sun go through its red giant phase and see what happens to planets at Earth's orbital distance, because the process takes hundreds of millions of years. We can observe stars at various stages of evolution, including red giants, and we can observe planets around some of them. But we cannot follow a single system through the entire process to see exactly what happens. There are also factors that might influence Earth's fate that are even harder to predict. For example, interactions with other planets could alter Earth's orbit. Jupiter, the most massive planet in the solar system, exerts gravitational influence on Earth, as Jupiter's own orbit changes during the Sun's red giant phase. It might perturb Earth's orbit in ways that could either help or hinder Earth's survival. Additionally, the Sun itself might undergo variations and instabilities during its red giant phase. The outer layers of a red giant star can pulsate, varying in size and temperature on timescales of months or years. These pulsations might affect the rate of mass loss or the density of the outer envelope, which in turn could affect Earth's orbital evolution. Despite all these uncertainties, there is a growing consensus among astronomers that Earth's prospects for survival are not good. While we cannot say with absolute certainty that Earth will be destroyed, the majority of recent models suggest that engulfment is the most likely outcome. Earth will probably not survive as an intact planet orbiting outside the Sun. But let us consider what would happen in each scenario, starting with the less likely but more hopeful case where Earth does survive. If Earth manages to avoid being consumed, what would it be like? Even if Earth remains outside the Sun's physical surface, it would be transformed beyond recognition. The intense heat from the nearby red giant would raise surface temperatures to thousands of degrees Celsius. Any remaining atmosphere would be completely stripped away by the intense solar wind and radiation. The surface would melt, becoming an ocean of molten rock. All evidence of Earth's long history would be erased. The continents, the ocean basins, the mountains, all would melt and flow together into a uniform molten sphere. Every trace of the life that once flourished here, every fossil, every remnant of human civilization, if any still existed, would be destroyed. Over time, as the molten Earth slowly cooled, it would solidify into a barren ball of rock, probably similar in appearance to Mercury or the Moon today. It would be airless, waterless, lifeless, orbiting a white dwarf star that was once the Sun. This remnant Earth would be a dead world, but it would still exist as a distinct object, a survivor of the cataclysm that destroyed the inner solar system. Now, let us consider the more likely scenario. Earth is engulfed by the expanding Sun. What would this process look like, and what would be Earth's ultimate fate as the Sun expands and its outer layers reach Earth's orbit? Earth would first encounter extremely tenuous gas, so thin that it would barely qualify as an atmosphere by terrestrial standards. But even this thin material would have effects. The drag would begin to slow Earth in its orbit, causing it to spiral inward. The outer reaches of Earth's own atmosphere, if any still remained at this point, would be heated to incandescence by friction with the solar material. As Earth continued to spiral inward, it would encounter progressively denser layers of the Sun's envelope. The drag would increase and Earth's inward spiral would accelerate. The surface temperature would rise to tens of thousands of degrees. Any solid material would vaporize. Earth would begin to leave a trail of vaporized rock and metal in its wake, like a comet leaving a tail. Earth's gravity might hold the planet together for a time, even as its surface boiled away into space. But as Earth plunged deeper into the Sun, approaching the denser inner regions of the envelope, the combination of extreme temperatures, intense tidal forces, and drag would overwhelm even Earth's gravity. The planet would be torn apart. The rocky mantle and metal core would fragment into countless pieces, each piece continuing to vaporize in the extreme heat. The atoms that once made up mountains and oceans, continents and creatures would be reduced to individual atoms of silicon, oxygen, iron, magnesium, and other elements, mixing with the hydrogen and helium of the Sun's outer layers. Eventually, all that would remain of Earth would be a slight enhancement in the concentration of heavy elements in a small region of the Sun's envelope. Even this signature would gradually diffuse and spread out until it was undetectable. Earth would cease to exist as a distinct entity, its matter incorporated into the Sun itself. When the Sun later sheds its outer layers to form a planetary nebula, some of Earth's atoms would be blown off into space along with the Sun's own material. These atoms would mix with the interstellar medium, perhaps eventually being incorporated into new stars, new planets, maybe maybe new life in some distant future. In this sense, Earth would not be truly destroyed, but transformed and recycled, its matter continuing to exist even though the planet itself would be gone. There is a certain poetry in this fate. Earth was born from the same cloud of gas and dust that formed the Sun 4.6 billion years ago. If Earth is consumed by the Sun, it would, in a sense, return to its parent star, closing a circle that began with the formation of the solar system. For those who find this fate troubling, it is worth remembering several important points. First, this will not happen for approximately 5 billion years. This is an almost incomprehensible amount of time. All of recorded human history, from the first civilizations to the present day, spans only about 10,000 years. 5 billion years is 500,000 times longer than all of human history. The universe itself is only about 13.8 billion years old. 5 billion years is more than 1/3 the current age of the universe. Second, Earth will become uninhabitable long before it is potentially consumed by the Sun, as we discussed earlier. The gradual brightening of the Sun during its late main sequence phase will trigger a runaway greenhouse effect in approximately 1 billion years. The oceans will evaporate, and Earth will become a sterile hothouse world. Any life that still exists will be extinguished billions of years before the Sun becomes a red giant. Third, if humanity or any descendants of humanity still exist 1 billion years from now, we will almost certainly have long since left Earth and spread to other worlds. A civilization that can survive for 1 billion years would have technological capabilities that seem like magic to us. We might have moved Earth to a more distant orbit, or built vast space habitats, or migrated to other star systems entirely. The question of Earth's physical survival during the Sun's red giant phase might be irrelevant to whatever our descendants have become. Finally, Earth's eventual destruction, whether by being consumed by the Sun or by being transformed into a scorched molten remnant, is simply part of the natural cycle of the universe. Everything that has a beginning has an ending. Stars are born, shine for a time, and die. Planets form, evolve, and are eventually destroyed or transformed. Even galaxies collide and merge. The universe is not static, but constantly changing, constantly cycling matter and energy through different forms. Earth's fate is shared by countless other planets throughout the galaxy and the universe. Every planet orbiting a sun-like star will face a similar reckoning when its star becomes a red giant. Some will be destroyed, others might survive in altered form, but none will remain unchanged. This is not a tragedy specific to Earth, but a universal reality. The question of whether Earth will survive the Sun's red giant phase remains open, and will likely remain somewhat uncertain until we have better models and observations of similar systems. But based on our current understanding, the most probable answer is no. Earth will likely be consumed, vaporized in the outer layers of the Sun, its atoms scattered and eventually recycled into new cosmic structures. But this fate lies so far in the future, across such vast expanses of time, that it has no bearing on the present or foreseeable future. For now, Earth is a vibrant living world, orbiting a stable, middle-aged star. We have billions of years ahead of us, time enough for evolution to produce entirely new forms of life. Time enough for humanity or its descendants to reach the stars. Time enough for possibilities we cannot even imagine. The ultimate fate of Earth reminds us that nothing lasts forever, but it also reminds us of our connection to the cosmos. We are made of atoms forged in ancient stars, living on a planet that will someday return its matter to the universe. We are temporary manifestations of the universe contemplating itself, and that makes each moment, each generation, each era of Earth's long history precious and worth cherishing. When the Sun's red giant phase finally ends, it will undergo one of the most beautiful and poignant transformations in all of astronomy. The star that has dominated our sky and sustained life on Earth for billions of years will shed its outer layers like a butterfly emerging from a cocoon, leaving behind a dense, glowing core that will slowly fade over timescales longer than the current age of the universe. To understand this final act in the Sun's biography, we need to follow the sequence of events that will unfold after the red giant phase reaches its conclusion. As we discussed earlier, the Sun will spend approximately 100 million years as a red giant, fusing helium into carbon and oxygen in its core, while also burning hydrogen in a shell surrounding that core. But helium, like hydrogen before it, is not an infinite fuel source. The core of the red giant Sun is relatively small and contains only a limited amount of helium. Eventually, after roughly 100 million years of fusion, the helium in the core will be exhausted. When the helium runs out, the core once again becomes inert. It is now composed primarily of carbon and oxygen, the products of helium fusion. These elements sit there, unable to fuse further because the temperature in the core is not high enough to initiate carbon fusion. Carbon fusion requires temperatures of around 600 million degrees Celsius, and the Sun's core will never reach this threshold. The Sun simply does not have enough mass to compress its core to the densities and temperatures needed for carbon to fuse. More massive stars, those with perhaps 8 to 10 times the mass of the Sun or more, can continue fusing heavier and heavier elements. Their cores become hot enough to fuse carbon into neon and magnesium, then neon into oxygen and magnesium, then oxygen into silicon and sulfur, and finally silicon into iron. But the Sun will never follow this path. Its fusion journey ends with carbon and oxygen. With no fusion occurring in the core, there is once again nothing to generate the outward pressure needed to balance gravity. The carbon-oxygen core begins to contract. As it contracts, it heats up, just as the helium core did before it. This heating ignites helium fusion in a shell around the carbon-oxygen core. So now the Sun has an even more complex layered structure, a carbon-oxygen core, surrounded by a helium-fusing shell, surrounded by a hydrogen-fusing shell, all within the extended envelope of the red giant. This configuration is highly unstable. The two fusing shells do not burn steadily. Instead, they undergo episodes of increased activity followed by periods of relative quiescence. The energy output varies dramatically, causing the outer layers of the Sun to pulsate. The Sun grows and shrinks, brightens and dims, on timescales of months to years. These pulsations become increasingly violent. The outer envelope of the Sun, already loosely bound because it is so extended and far from the core, begins to be lifted off the star entirely. Each pulsation sends shock waves through the envelope, and with each pulsation, some material is blown away into space. At the same time, the intense radiation from the hot core and fusing shells exerts pressure on the overlying material through a process called radiation pressure. Light itself, photons streaming outward from the interior, can push on atoms and drive them away from the star. This radiation pressure becomes extremely effective in the outer layers of evolved giant stars, where the material is already tenuous and weakly bound. The combination of pulsations and radiation pressure creates a powerful stellar wind, far more intense than anything the Sun experienced during its main sequence or early red giant phase. Material streams away from the Sun at speeds of tens of kilometers per second. The mass loss rate accelerates. The Sun might lose the equivalent of Earth's mass every 1,000 years, or every few hundred years. This does not sound like much compared to the Sun's total mass, but it adds up quickly. Over a period of perhaps tens of thousands to hundreds of thousands of years, the Sun sheds a significant fraction of its remaining mass. The outer envelope, which contained most of the Sun's volume but only a fraction of its mass, is blown away into space. Layer after layer is peeled off and cast into the surrounding void. This ejected material does not simply disappear, it forms an expanding shell of gas surrounding the remnant of the Sun. This shell is illuminated from within by the intense ultraviolet radiation coming from the hot core that remains at the center. The ultraviolet light energizes the atoms in the shell, causing them to glow with characteristic colors. Hydrogen glows red, oxygen glows blue-green, nitrogen glows red, and so on. The result is one of the most beautiful phenomena in astronomy, a planetary nebula. The name planetary nebula is somewhat misleading. These objects have nothing to do with planets. The name comes from early astronomers who, looking through small telescopes, thought these fuzzy, round, glowing objects resembled planets like Uranus or Neptune. We now know they are nothing like planets, but the name has stuck. Planetary nebulae come in an astonishing variety of shapes and forms. Some are nearly perfect spheres, shells of glowing gas expanding symmetrically in all directions. Others are elongated, forming elliptical or cylindrical shapes. Some have intricate internal structures with knots and filaments of denser material. Others have bipolar shapes with two lobes of material streaming outward in opposite directions, resembling an hourglass or a butterfly. The exact shape of a planetary nebula depends on many factors: the rotation of the original star, the presence of magnetic fields, whether the star had a binary companion, and the details of how the mass was lost. In the case of the Sun, which is a solitary star without a close companion, the planetary nebula will likely be relatively simple in structure, perhaps a roughly spherical or slightly elliptical shell. This planetary nebula will be spectacular. From a distance of many light years, it would appear as a glowing cloud of gas, perhaps a light year or more in diameter, with intricate colors and structures. At its center would be visible a brilliant point of light, the exposed core of the Sun. The planetary nebula will expand outward at speeds of tens of kilometers per second. As it expands, it will gradually become larger and more diffuse. The density will drop, and eventually, after tens of thousands of years, the nebula will become so thin that it is no longer visible. It will merge with the surrounding interstellar medium, adding its material to the great reservoir of gas and dust that fills the space between stars. This material is enriched with heavy elements. The Sun has spent billions of years converting hydrogen into helium and helium into carbon and oxygen. These elements, along with trace amounts of nitrogen, neon, and others produced in various nuclear reactions, are now being returned to the galaxy. This enriched material will eventually be incorporated into new generations of stars and planets, continuing the cosmic cycle of stellar birth, death, and rebirth. But what about the core itself, the brilliant point of light at the center of the planetary nebula? This is what the Sun becomes after the red giant phase, a white dwarf star. When the Sun has finished shedding its outer layers, all that remains is the core, composed primarily of carbon and oxygen. This core has a mass of perhaps 50 to 60% of the Sun's original mass. In other words, the Sun will lose 40 to 50% of its mass during its red giant and planetary nebula phases, blowing it off into space. Despite containing about half the Sun's original mass, the white dwarf is incredibly small. It has a radius of only about 7,000 kilometers, roughly the same size as Earth. To put this in perspective, the current Sun has a radius of about 700,000 kilometers. The white dwarf is 100 times smaller in radius, yet contains half the mass. This makes it extraordinarily dense. The density of a white dwarf is approximately 1 million times the density of water. A single teaspoon of white dwarf material, if you could somehow bring it to Earth, would weigh about 5 tons. This is matter compressed to a state unlike anything we experience in everyday life. A state where atoms are crushed so tightly together that the normal structure of matter breaks down. In ordinary matter, atoms consist of nuclei surrounded by clouds of electrons, with vast amounts of empty space in between. In a white dwarf, the pressure is so intense that the electron clouds are stripped away, and the electrons are compressed into a dense sea surrounding the atomic nuclei. The electrons are packed so tightly that quantum mechanical effects become dominant. As we mentioned earlier when discussing the helium flash, electrons are fermions and obey the Pauli exclusion principle. No two electrons can occupy the same quantum state. When electrons are squeezed together as tightly as they are in a white dwarf, they fill up all the available Lagrange quantum states and are forced into higher and higher energy states. This creates what is called electron degeneracy pressure. This degeneracy pressure is not thermal pressure that depends on temperature. It is a purely quantum mechanical pressure that depends only on density. It is this degeneracy pressure that supports the white dwarf against gravitational collapse. The white dwarf does not need to generate energy through fusion or any other process to hold itself up. The quantum mechanical properties of electrons provide all the support it needs. When the white dwarf is first exposed at the center of the planetary nebula, it is extraordinarily hot. Its surface temperature might be 100,000 degrees Celsius or even higher, much hotter than the current Sun's surface temperature of about 5,500 degrees Celsius. At these temperatures, the white dwarf shines with brilliant white or even bluish light, hence the name white dwarf. This heat is not being generated by fusion. There is no fusion occurring in a white dwarf. The white dwarf is not actively generating energy. It is simply radiating away the residual heat from its formation, slowly cooling like a hot coal removed from a fire. Because the white dwarf is not generating new energy, it must inevitably cool. But this cooling process is extremely slow because the white dwarf is so dense. It has an enormous heat capacity. Even though it is radiating energy into space continuously, it contains so much thermal energy that it will take an extraordinarily long time to cool down, over billions of years. The white dwarf that was once the Sun will slowly fade and cool. Its surface temperature will drop from 100,000 degrees to 50,000 degrees, then to 20,000 degrees, then to 10,000 degrees. Its color will change from brilliant blue-white to yellow to orange to red. After approximately 1 billion years of cooling. The white dwarf will have a surface temperature similar to the current Sun's surface temperature, around 5,000 to 6,000 degrees Celsius. But it will be far smaller and therefore far less luminous than the current Sun. It will shine with only a tiny fraction of the Sun's current brightness. The cooling continues. After 10 billion years, the white dwarf will have cooled to perhaps 2,000 or 3,000 degrees Celsius, glowing with a dull red light. After 100 billion years, it might cool to just a few hundred degrees, barely glowing at all. Eventually, after trillions of years, the white dwarf will cool to the point where it no longer emits visible light. It will become what astronomers call a black dwarf, a cold, dark cinder composed of crystallized carbon and oxygen. It will be invisible except for the faint infrared radiation it emits and the gravitational influence it exerts on anything nearby. However, this final state lies so far in the future that it is almost meaningless to contemplate. The universe is currently about 13.8 billion years old. Even the oldest white dwarfs in the universe, which formed when the universe was only a few billion years old, have not yet cooled to become black dwarfs. They are still warm enough to emit at least some detectable light. It will take perhaps 10 trillion to 100 trillion years for white dwarfs to cool completely to the black dwarf state. To put this timescale in perspective, 10 trillion years is about 700 times longer than the current age of the universe. By the time the Sun becomes a black dwarf, the universe will be unrecognizably different from what it is today. Most stars will have burned out. Galaxies will have collided and merged. The universe will be a cold, dark and lonely place, populated mainly by stellar remnants like black dwarfs, neutron stars and black holes. But let us return to the nearer-term future, to the time when the Sun first becomes a white dwarf. What will the solar system look like with a white dwarf at its center instead of the Sun? Any planets that survive the red giant phase, likely Mars and the outer planets, will continue to orbit the white dwarf just as they orbited the Sun before. However, the white dwarf will provide almost no heat. Even though it is initially very hot, it is so small that it emits very little total energy. The planets will be frozen, receiving almost no warmth from their star. Mars, if it survives, will be colder than it has ever been. Any atmosphere it might have retained or temporarily gained during the red giant phase will freeze out onto the surface. It will be a dead, frozen world orbiting a faint point of light. The outer planets, Jupiter, Saturn, Uranus and Neptune, will also be frozen and dark. Their atmospheres might undergo interesting changes as they cool, possibly forming exotic ices or even snowing out some of their atmospheric components. But they will be cold, dark, and lifeless. The moons of these planets, which might have briefly enjoyed warmth and even habitability during the Sun's red giant phase, will freeze solid once again. Any liquid water that appeared on Europa or Enceladus or other icy moons will freeze, locking those worlds back into the deep freeze from which they briefly emerged. The solar system will be a graveyard, a collection of cold, dark worlds orbiting the slowly cooling remnant of their star. There will be no warmth, no light sufficient for photosynthesis, no energy to drive weather or geological activity beyond, perhaps, the slow radioactive decay in planetary interiors. This might seem like a depressing fate, but it is important to remember that this is not unique to our solar system. This is the destiny of every planetary system around every sun-like star in the universe. Billions upon billions of stars will go through this same transformation, each creating a planetary nebula and leaving behind a white dwarf. In fact, there is something beautiful and even hopeful about this fate. The planetary nebula that the Sun creates will enrich the interstellar medium with heavy elements. Carbon, oxygen, nitrogen, and other elements created in the Sun over its lifetime will be scattered into space. These elements are essential for planets and for life. When the first generation of stars formed in the early universe, they were composed almost entirely of hydrogen and helium, the primordial elements created in the Big Bang. These stars had no planets like Earth because there were no heavy elements to make rocky planets from. When these first stars died, they scattered heavy elements into space. Successive generations of stars formed from increasingly enriched material. The Sun itself is a third or later generation star. It formed from material that had been enriched by previous generations of stars. The carbon in your body, the oxygen you breathe, the iron in your blood, the calcium in your bones, all of these elements were created in stars that lived and died before the Sun was born. When the Sun dies and creates its planetary nebula, it will contribute to the ongoing enrichment of the galaxy. The material it scatters into space might, billions of years in the future, become part of new stars and new planets. Perhaps some of those planets will be home to life. Perhaps some of that life will develop intelligence and consciousness, and look up at their sky and wonder about their place in the cosmos, just as we do. In this sense, the Sun does not truly die, it transforms. The matter and energy that make up the Sun will continue to exist in new forms. The white dwarf will persist for trillions of years, a monument to the star that once was. The scattered nebula will seed new generations of stars and planets, and the light that the Sun emitted over its 10 billion year lifespan will continue traveling outward through space, potentially being seen by observers in distant galaxies for billions of years after the Sun itself has become a white dwarf. The transformation of the Sun from a main sequence star to a red giant to a planetary nebula and finally to a white dwarf is one of the fundamental pathways of cosmic evolution. It is how the universe recycles matter, how heavy elements are created and distributed, how the raw materials for planets and life are manufactured and scattered throughout the galaxy. Understanding what the Sun becomes after its red giant phase helps us understand our connection to the broader cosmos. We are not separate from the universe, but intimately connected to it. We are made of material processed through multiple generations of stars. We exist because stars lived and died, creating the elements that make up our world and our bodies. The white dwarf that the Sun will eventually become represents both an ending and a continuation. It is the end of the Sun as an active, energy-generating star. But it is also a continuation of the Sun's matter and energy in a new form. A form that will persist 4 timescales that dwarf even the Sun's own lifetime, as that white dwarf slowly cools over trillions of years, gradually fading from brilliant white to dim red to eventual darkness. It will be a reminder of the Sun that once was, the star that made the solar system, that allowed life to emerge on Earth, that shone in our sky for billions of years, and surrounding it, expanding ever outward, will be the glowing nebula of the Sun's outer layers. A beautiful memorial to a star that gave life to at least one world and perhaps, through the elements it created and scattered, will give rise to life on worlds yet to be born. This is what the Sun becomes after the red giant phase ends, a slowly cooling white dwarf at the center of an expanding planetary nebula, a stellar remnant that will persist for trillions of years. A contribution to the ongoing cycle of stellar birth and death that has been shaping the universe since the first stars ignited in the darkness of the early cosmos. When the red giant phase finally comes to an end, the Sun will undergo one of the most beautiful transformations in all of nature. What remains will be something profoundly different from the brilliant yellow star we know today. Yet it will carry forward the essence of what the Sun was, preserving it in a form that will endure 4 timescales that make the Sun's current lifetime seem brief by comparison. To understand what the Sun becomes, we need to follow the final stages of its evolution as a red giant. As we discussed, the Sun will spend roughly 100 million years as a red giant, fusing helium into carbon and oxygen in its core. But this helium fuel, like the hydrogen before it, is finite. The core is relatively small and contains only limited amounts of helium to fuse. When the helium in the core is exhausted, fusion there stops. The core, now composed primarily of carbon and oxygen, becomes inert. These elements simply sit there, unable to fuse because the temperature is not high enough. Fusing carbon requires temperatures around 600 million degrees Celsius, and the Sun's core will never reach this extreme. Only stars significantly more massive than the Sun, perhaps 8 times the Sun's mass or greater, can achieve the conditions necessary for carbon fusion. So the Sun's fusion journey ends with carbon and oxygen. It cannot go further up the periodic table. It cannot create the heavier elements like neon, magnesium, silicon, or iron that more massive stars produce in their final years. The Sun's nuclear alchemy stops here. With fusion halted in the core, there is nothing generating the outward pressure needed to balance gravity's inward pull. The carbon-oxygen core begins to contract. As it contracts, it heats up from the compression, and this heat spreads to the layers immediately surrounding the core. These layers still contain helium, and when they heat up sufficiently, helium fusion ignites in a shell around the inert core. The Sun now has a remarkably complex internal structure. At the very center sits the carbon-oxygen core, inert and contracting. Around this core is a shell where helium is fusing into more carbon and oxygen. Outside that is another shell where hydrogen is still fusing into helium. And surrounding all of this is the vast extended envelope of the red giant, reaching perhaps 100 million kilometers or more from the center. This configuration is inherently unstable. The two burning shells do not operate smoothly and steadily. Instead, they undergo cycles of activity. Sometimes one shell dominates, sometimes the other. The energy output fluctuates dramatically. These fluctuations cause the outer envelope of the Sun to pulsate, expanding and contracting rhythmically. Imagine the Sun breathing, growing larger and smaller, brighter and dimmer, in a cosmic rhythm that repeats over months or years. Each time the Sun expands, its outer layers move farther from the core. Each time it contracts, they fall back inward. But with each cycle, some material does not fall back. Some is lifted high enough and given enough energy that it escapes the Sun's gravity entirely. These pulsations grow more violent over time. The outer envelope, already loosely bound because it extends so far from the dense core, begins to be stripped away. Material streams off into space, blown away by the combination of pulsations and intense radiation pressure from the hot interior. This mass loss accelerates. What begins as a gentle stellar breeze becomes a fierce gale. The Sun might lose the equivalent of Earth's entire mass every few hundred or few thousand years. This sounds slow compared to human timescales, but it is extraordinarily rapid for a star. The outer layers are being torn away and cast into the void. Over perhaps 50,000 to 100,000 years, a substantial portion of the Sun's remaining mass is ejected. The enormous envelope that made the Sun a red giant, the layers that extended across millions or even hundreds of millions of kilometers, is blown away into space. Layer after layer peels off like the layers of an onion, each one carried outward by the relentless pressure of light and the violent pulsations. This ejected material does not disappear. It forms an expanding shell of gas surrounding what remains of the Sun. Initially, this shell is invisible, just hot gas spreading outward in darkness. But at the center, the core of the Sun is being progressively exposed as the overlying layers are stripped away. And this core is extraordinarily hot. When the core is finally laid bare, it has a surface temperature that might exceed 100,000 degrees Celsius, perhaps even reaching 150,000 or 200,000 degrees in some cases. This is far hotter than the surface of the current Sun, which sits at a relatively cool 5,500 degrees Celsius. This intensely hot core floods the surrounding space with ultraviolet radiation, radiation so energetic that it is invisible to human eyes. This ultraviolet light streams outward and strikes the expanding shell of ejected material. When ultraviolet photons collide with atoms in the shell, they knock electrons loose, ionizing the atoms and energizing them. The energized atoms emit light at specific wavelengths corresponding to their electronic transitions. Hydrogen emits deep red light, oxygen emits blue-green light, nitrogen emits red, sulfur emits red and blue. The combination of emissions from different elements creates a spectacular palette of colors. The expanding shell begins to glow with brilliant, vivid colors, illuminated from within by the tiny, intensely hot core at its center. This glowing shell of gas is called a planetary nebula, one of the most beautiful phenomena in the cosmos. The name planetary nebula is a historical accident and rather misleading. Early astronomers observing these objects through small telescopes thought they looked somewhat like planets, appearing as fuzzy round disks rather than as point-like stars. We now know they have nothing whatsoever to do with planets, but the name persists. Planetary nebulae display an astonishing variety of shapes and structures. Some are nearly perfect spheres, symmetric shells expanding uniformly in all directions. Others are elongated into elliptical or cylindrical forms. Some have bipolar structures, with two lobes of material streaming outward in opposite directions, like an hourglass or butterfly. Others have intricate internal structures with knots, filaments, and complex patterns. The shape depends on many factors. If the star was rotating, the rotation can create asymmetries in how material is ejected. Magnetic fields threading through the star can channel material along specific directions. If the star had a companion star orbiting it, the gravitational influence of that companion can shape the outflow. The details of the pulsations and mass loss also play a role. The Sun, being a solitary star without a close companion and rotating relatively slowly, will likely produce a planetary nebula that is fairly simple and symmetric. It might be roughly spherical or perhaps slightly elliptical, without the dramatic bipolar shapes seen in some nebulae. But even a simple planetary nebula would be magnificent. Viewed from a distance of several light years, it would appear as a glowing shell, perhaps half a light year to a full light year in diameter, roughly 10 trillion kilometers across. The shell would glow with colors dominated by the red of hydrogen and the blue-green of oxygen, creating beautiful hues ranging from pink to turquoise. At the very center would be visible a brilliant blue-white point of light, the exposed core of the Sun. The planetary nebula expands outward at speeds typically between 20 and 50 kilometers per second. At these speeds, the nebula grows larger over time. After 10,000 years, a nebula expanding at 30 kilometers per second would be about 10 trillion kilometers across, roughly 1 light-year in diameter. After 50,000 years, it would be 5 light-years across. As the nebula expands, it becomes increasingly tenuous. The same amount of material is spread over an ever larger volume, so the density decreases. Eventually, after tens of thousands of years, the nebula becomes so thin that it is no longer dense enough to glow brightly. The beautiful colors fade. The nebula merges with the surrounding interstellar medium, becoming indistinguishable from the general sea of gas and dust that fills the space between stars. But while the nebula fades and disperses, it leaves a lasting impact. The material ejected by the Sun is enriched with elements heavier than the hydrogen and helium that dominated the original composition. Carbon and oxygen, created through helium fusion, are abundant. There are also traces of nitrogen, created through hydrogen fusion in the outer layers. Small amounts of other elements like neon, magnesium, and silicon are present as well. This enriched material mixes with the interstellar medium, raising the overall concentration of heavy elements in the local environment. Millions or billions of years in the future, this material might be incorporated into new clouds of gas and dust. These clouds might collapse to form new generations of stars and planets. Those planets might be richer in the elements needed for rocky worlds and for life, thanks in part to the contribution from the Sun. In this way, the Sun contributes to the ongoing chemical enrichment of the galaxy. Every generation of stars creates heavier elements and returns them to space. Each new generation of stars forms from slightly enriched material and continues the process. This cosmic recycling has been happening since the first stars formed billions of years ago, and it will continue for billions or even trillions of years into the future. Now, let us turn our attention to the core itself, the brilliant point of light at the center of the planetary nebula. This is what the Sun directly becomes when the red giant phase ends. This is the final stable form that the Sun will take. This is a white dwarf star. The white dwarf contains roughly 50 to 60% of the Sun's original mass. The rest, 40 to 50% of the mass the Sun had when it formed, has been blown away during the red giant and planetary nebula phases. Despite containing about half the Sun's mass, the white dwarf is astonishingly small. Its radius is approximately 7,000 kilometers, give or take a few thousand kilometers, depending on its exact mass and composition. To put this in perspective, Earth has a radius of about 6,400 kilometers. The white dwarf is only slightly larger than Earth. The current Sun, in contrast, has a radius of about 700,000 kilometers. The white dwarf is about 100 times smaller in radius than the Sun is now. Yet this Earth-sized sphere contains half the mass of the Sun. The density is almost beyond comprehension. A cubic centimeter of white dwarf material, a cube about the size of a sugar cube, would have a mass of roughly 1 million grams, or 1 metric ton. A teaspoon of white dwarf material would weigh about 5 tons on Earth. If you could somehow place a white dwarf on a gigantic scale, it would have a density about 1 million times that of water. How can matter be compressed to such extreme densities? The answer lies in the structure of atoms and the quantum nature of electrons. In ordinary matter, atoms consist of tiny nuclei surrounded by electron clouds, with vast amounts of empty space between atoms. When you touch a table, you feel it as solid because the electron clouds of your hand's atoms repel the electron clouds of the table's atoms through electromagnetic forces, but most of the volume is actually empty space. In a white dwarf, the pressure is so immense that this normal atomic structure is crushed. The electron clouds are stripped away from the nuclei. The matter becomes a plasma of positively charged nuclei swimming in a sea of electrons, all packed together far more tightly than in ordinary matter. The electrons are compressed so tightly that quantum mechanical effects dominate. Electrons are fermions, particles that obey the Pauli exclusion principle, which states that no two electrons can occupy exactly the same quantum state. In normal matter, this principle does not impose significant constraints because there are far more available quantum states than there are electrons to fill them. But in a white dwarf, the density is so high that the electrons are forced into every available Lagrange quantum state. When all the Lagrange states are filled, additional electrons must occupy higher energy states. The electrons resist being compressed further, not because of thermal effects or electromagnetic repulsion, but because quantum mechanics forbids them from being squeezed into already occupied states. This creates what physicists call electron degeneracy pressure. This pressure depends only on the density of electrons, not on temperature. It is a purely quantum mechanical phenomenon that has no analog in our everyday experience. And it is this degeneracy pressure that supports the white dwarf against gravitational collapse. Unlike a normal star, which must continually generate energy through fusion to maintain the pressure needed to support itself, a white dwarf requires no energy source. The quantum mechanical properties of electrons provide all the support needed. The white dwarf can sit in equilibrium indefinitely, with gravity's inward pull exactly balanced by electron degeneracy pressure's outward push. When the white dwarf is first exposed at the center of the planetary nebula, it is phenomenally hot. Its surface temperature might be 100,000 degrees Celsius or even higher, reaching temperatures of 150,000 or 200,000 degrees in extreme cases. This makes it one of the hottest stellar surfaces in the galaxy, far hotter than massive blue supergiant stars. At these temperatures, the white dwarf emits most of its light in the ultraviolet part of the spectrum, invisible to human eyes, but it also emits intense visible light, particularly at the blue end of the spectrum. It would appear as a brilliant blue-white star, dazzling in its intensity despite its small size. This extreme heat is not being generated by any ongoing fusion reactions. There is no fusion occurring in a white dwarf. The core is too cool for carbon fusion, and there is no remaining hydrogen or helium to fuse. The white dwarf is not actively producing energy. Instead, it is radiating away thermal energy stored from its formation, like a hot coal that has been removed from a fire. The white dwarf begins to cool. Photons carry energy away from its surface, escaping into space. Gradually, very gradually, the temperature drops, but this cooling process is extraordinarily slow because the white dwarf has an enormous heat capacity. It contains an immense amount of thermal energy, and even though it is continuously radiating, it will take billions of years to cool significantly. But after about 10 million years, the surface temperature might drop from 200,000 degrees to 100,000 degrees. The white dwarf is still blue-white and incredibly hot, but it has cooled somewhat. After 100 million years, it might cool to 50,000 degrees. After a billion years, its surface temperature might be around 20,000 degrees, still much hotter than the current sun. As it cools, its color changes. The brilliant blue-white gradually shifts toward pure white, then to yellow-white, then to orange, and eventually to red. After several billion years, the white dwarf might have a surface temperature similar to the current sun, around 5,000 to 6,000 degrees Celsius, giving it a yellowish color. But even though its temperature might be similar to the current sun's temperature, its luminosity, its total energy output, would be far less. Luminosity depends on both temperature and surface area. The white dwarf is so small that even at relatively high temperatures, it does not emit much total energy. A white dwarf with the sun's current surface temperature would be only about 1% as luminous as the sun is today, perhaps even less. The cooling continues inexorably. After 10 billion years, the white dwarf might have cooled to perhaps 3,000 degrees, glowing with a dull red light. After 100 billion years, its temperature might drop to just a few hundred degrees, barely emitting any visible light at all. Eventually, after timescales measured in trillions of years, the white dwarf will cool to the point where it emits no visible light. Its surface temperature will drop to near absolute zero. At this point, it becomes what astronomers call a black dwarf, a cold, dark sphere of degenerate matter composed of crystallized carbon and oxygen. The white dwarf does not remain entirely gaseous as it cools. At some point, when the temperature drops below a critical threshold that depends on density and composition, the carbon and oxygen nuclei arrange themselves into a crystal lattice. The white dwarf begins to solidify from the inside out, forming what is essentially a gigantic cosmic diamond or graphite crystal, depending on the exact structure the carbon atoms adopt. This crystallization releases latent heat, much as water releases heat when it freezes. This additional heat source slows the cooling process somewhat, extending the time it takes for the white dwarf to reach its final cold state. However, the black dwarf stage lies so far in the future that it is almost meaningless to discuss. The universe is currently about 13.8 billion years old, even the oldest white dwarfs in existence, which formed when the universe was only a few billion years old, are still warm enough to emit detectable light. No white dwarf has yet cooled to become a black dwarf, and none will for trillions of years. To put this in perspective, it will take at least 10 trillion years for a white dwarf to cool completely to the black dwarf state, possibly much longer. This is about 700 times the current age of the universe. By the time the Sun becomes a black dwarf, the universe will be unimaginably different. Most stars will have burned out. Galaxies will have collided and merged. Star formation will have ceased as the available gas is exhausted. The universe will be a cold, dark, and nearly empty place. But for the foreseeable future, meaning the next many billions of years, the white dwarf that was once the Sun will be a visible object, slowly cooling and fading, but still shining with residual heat. What will the solar system look like with this white dwarf at its center? Any planets that survive the red giant phase will continue to orbit the white dwarf. Their orbits will be essentially the same as before, following the same paths they did when the Sun was a main sequence star or a red giant. Kepler's laws of orbital motion do not care about the size or temperature of the central object, only about its mass, and the white dwarf retains about half the Sun's original mass. However, the planets will receive almost no heat from the white dwarf. Even though the white dwarf is initially very hot, it is so small that it emits very little total energy. The amount of heat and light reaching any planet will be negligible compared to what the Sun provides today. Mars, if it survives, will be frozen far beyond anything it experiences today. Its thin atmosphere, if any remains, will freeze out onto the surface. The carbon dioxide that makes up most of Mars' current atmosphere will form dry ice at the poles and in shadowed regions. Any water ice will be locked in permanent deep freeze. The surface temperature might drop to just a few dozen degrees above absolute zero. The outer planets, Jupiter, Saturn, Uranus, and Neptune, will also be frozen and dark. They might retain some internal heat from their formation and from the decay of radioactive elements in their cores, but they will receive essentially no energy from the white dwarf. Their atmospheres will cool dramatically. Gases might condense and freeze out, snowing onto lower layers or forming exotic ices. The moons of the outer planets, which might have briefly enjoyed warmth during the Sun's red giant phase, will freeze solid once again. Europa's subsurface ocean, if it still exists, will freeze completely. Titan's lakes of liquid methane and ethane might freeze as well, depending on how much internal heat these moons retain. Enceladus, with its geysers fed by tidal heating from Saturn, might continue to have some activity, but the surface will be far colder than it is today. The solar system will be a graveyard, a collection of frozen, lifeless worlds orbiting the faintly glowing remnant of their star. There will be no seasons, no weather driven by solar heating, no possibility of life as we know it. It will be a realm of eternal cold and darkness, illuminated only by the dim light of distant stars and the faint glow of the white dwarf. This might seem like a melancholy fate, but it is also strangely peaceful. The violent transformations of the red giant phase will be over. The dramatic mass loss and the creation of the planetary nebula will have passed. What remains will be stable and unchanging on human timescales, a quiet coda to the sun's long and energetic life. The white dwarf itself, though cooling, will remain fundamentally the same for trillions of years. It will not collapse further. It will not undergo any dramatic transformations. It will simply exist, supported by electron degeneracy pressure, slowly radiating away its heat into the void. It is a stable endpoint of stellar evolution, a final resting state for stars like the Sun. In a sense, the white dwarf is eternal, or as close to eternal as anything in the universe can be. While it will eventually cool to become a black dwarf, the timescales involved are so vast that, for all practical purposes, the white dwarf endures forever. Long after galaxies have aged and faded, long after star formation has ceased, long after the universe has become cold and dark, white dwarfs will still exist, monuments to the stars that once were. The transformation of the Sun from a vibrant, energy-generating star into a slowly cooling white dwarf is one of the fundamental pathways of cosmic evolution. It is the fate awaiting all stars with masses between about half the Sun's mass and about 8 times the Sun's mass. This encompasses the vast majority of stars in the universe. More massive stars meet more violent ends, exploding as supernova and leaving behind neutron stars or black holes. Less massive stars, red dwarfs with masses below about half the Sun's mass, evolve so slowly that none have yet reached the end of their main sequence lifetimes in the entire history of the universe. But for sun-like stars, for the countless yellow and orange dwarfs scattered throughout the galaxies, the white dwarf is the final destination. But understanding what the Sun becomes after the red giant phase connects us to the broader story of the universe. It shows us that stars, like all things, have finite lifetimes. They are born, they evolve, they age, and they die, or at least transform into something new. But in dying, they contribute to the ongoing enrichment and evolution of the cosmos. The elements scattered by the planetary nebula will seed new stars and planets. The white dwarf itself, though no longer a source of light and heat, remains a repository of processed matter, a dense concentration of carbon and oxygen created through billions of years of nuclear fusion, and the light emitted by the Sun over its 10 billion year lifetime will continue traveling outward through the universe, potentially visible to observers transfers billions of light years away long after the Sun itself has become a white dwarf. This is what the Sun becomes when the red giant phase ends. A white dwarf star, an Earth-sized sphere of incredibly dense matter supported by quantum mechanical pressure, initially blazing with intense heat, but slowly cooling over trillions of years. It is both an ending and a transformation, a final chapter in the Sun's story, but also a continuation of its existence in a new and stable form. It is a reminder that, while nothing lasts forever in its original form, the matter and energy of the universe continue, cycling through different states, contributing to the ongoing evolution of the cosmos from the Big Bang to whatever ultimate fate awaits the universe in the unimaginably distant future. The formation of a white dwarf is one of the most remarkable transformations in the universe. A process where a bloated, dying star sheds most of its mass and compresses what remains into an object no larger than Earth, but containing the mass of half a sun. To understand how this extraordinary object comes into being and to envision what our sun will look like when it becomes one, we need to follow the detailed sequence of events that unfold during the final stages of stellar evolution. The journey to becoming a white dwarf begins billions of years before the white dwarf itself appears. It starts when a star like the Sun exhausts the hydrogen fuel in its core and begins its transformation into a red giant. We have discussed this transformation before, but now we need to examine it specifically from the perspective of white dwarf formation, because every step in the red giant phase is preparing the star for its ultimate fate. When the Sun's core runs out of hydrogen, fusion there ceases. The core, now composed primarily of helium, contracts under gravity. This contraction heats the core, and the rising temperature ignites hydrogen fusion in a shell surrounding the helium core. The energy from this shell fusion pushes the Sun's outer layers outward, causing the Sun to swell into a red giant. At this stage, something crucial is happening in the core. As it contracts, the density increases dramatically. The helium nuclei and electrons are being squeezed closer and closer together. Eventually, the density becomes so extreme that quantum mechanical effects become important. The electrons enter a state called degeneracy. In ordinary matter, electrons orbit atomic nuclei in specific quantum states, and there is plenty of room for all the electrons to spread out. But when matter is compressed to extreme densities, the electrons run out of available low-energy quantum states. The Pauli exclusion principle, a fundamental law of quantum mechanics, states that no two electrons can occupy exactly the same quantum state. When all the low-energy states are filled, additional electrons must be forced into higher energy states. This creates a pressure that resists further compression, a pressure that depends only on density and not on temperature. This is electron degeneracy pressure, and it is fundamentally different from the thermal pressure that supports normal matter. Thermal pressure arises from particles bouncing around due to heat. Degeneracy pressure arises from a quantum mechanical prohibition against putting too many electrons in the same place. The helium core of the red giant Sun becomes electron degenerate, while it is still heating up. The core is contracting and getting hotter, but the degeneracy pressure prevents it from contracting as much as it would in a normal gas. The core reaches a state where it is supported primarily by degeneracy pressure rather than thermal pressure. Eventually, the temperature in the core reaches about 100 million degrees Celsius, hot enough for helium fusion to begin. In a normal, non-degenerate gas, the onset of fusion would cause the gas to expand and cool, creating a smooth transition. But in the degenerate core, something dramatic happens instead. The helium flash. When helium fusion begins in the degenerate core, it releases enormous amounts of energy. Normally, this energy would cause the core to expand, which would cool it down and regulate the fusion rate. But because the core is degenerate, the pressure does not depend on temperature. The core does not expand in response to the heating. Instead, the temperature rises dramatically. Higher temperature means faster fusion, which releases more energy, which raises the temperature even more. It is a runaway thermonuclear explosion occurring deep inside the star for a few seconds or minutes. The energy output from the core might reach hundreds of billions of times the Sun's current luminosity. This sounds catastrophic. And in a sense it is, but it happens so deep inside the star that the overlying layers absorb and dampen the explosion. The outer layers barely notice. The helium flash delivers enough energy to lift the core out of degeneracy. The core expands, becomes non-degenerate, and settles into a stable state where it is fusing helium into carbon and oxygen. The Sun now has a helium-burning core surrounded by a hydrogen-burning shell, all within its extended red giant envelope. This helium-burning phase lasts for approximately 100 million years. During this time, carbon and oxygen accumulate in the core as the ash of helium fusion. Eventually, the helium in the core is exhausted, and fusion there ceases. The core, now composed of carbon and oxygen, again becomes inert. Here is where the path to white dwarf formation truly begins in earnest. The carbon-oxygen core contracts under gravity, heating up as it does. If the Sun were more massive, perhaps 8 or 10 times its current mass, the core would eventually become hot enough to fuse carbon into heavier elements. But the Sun is not massive enough. The core will never reach the 600 million degrees or so needed for carbon fusion. As the core contracts, it becomes degenerate again, but now it is composed of carbon and oxygen rather than helium. Electron degeneracy pressure once again provides support against gravity. The core settles into a state where it is inert, not generating energy, but supported by quantum mechanical pressure. But the contraction of the core heats the overlying layers. Helium fusion ignites in a shell around the carbon-oxygen core. Outside that, hydrogen is still burning in its own shell. The Sun now has a degenerate carbon-oxygen core, a helium-burning shell, a hydrogen-burning shell, and a vast extended envelope reaching perhaps 100 million to 200 million kilometers from the center. This configuration is extraordinarily unstable. The two burning shells interact in complex ways, with each affecting the other's burning rate. The energy output fluctuates wildly. These fluctuations drive pulsations in the outer envelope. The envelope expands and contracts rhythmically like a beating heart, with periods ranging from months to years. These pulsations are not gentle. Each time the envelope expands, it lifts enormous amounts of material high above the core, working against gravity. Some of this material gains enough energy to escape entirely. Each pulsation strips away some of the outer layers, sending them streaming into space. At the same time, radiation pressure becomes increasingly important. The luminous core and burning shells emit intense radiation, and this radiation carries momentum. When photons are absorbed by atoms in the outer layers, they transfer their momentum to those atoms, pushing them outward. In the tenuous, extended outer envelope of an evolved red giant, radiation pressure can become strong enough to blow material away from the star. The combination of pulsations and radiation pressure creates a powerful stellar wind, far more intense than the gentle solar wind the Sun produces today. Material streams away from the Sun at speeds of tens of kilometers per second. The mass loss rate accelerates dramatically. The Sun might be losing the equivalent of 1/10,000th of its total mass per year, which sounds small but accumulates quickly. Over tens of thousands to perhaps 100,000 years, the Sun loses a substantial fraction of its remaining mass. The enormous envelope that made it a red giant is progressively stripped away. Layer after layer is torn off and cast into space. The burning shells, which were previously buried deep within the star, are gradually exposed as the overlying material is removed. This process accelerates as it continues. The less mass there is in the envelope, the less tightly it is bound to the core, and the easier it is for radiation pressure and pulsations to blow it away. What begins as rapid mass loss becomes even more rapid. The final stages of envelope ejection might occur over just a few thousand years or less. Eventually, the entire envelope is gone. All that remains is the core, the degenerate carbon-oxygen sphere that was hidden at the center of the red giant. This core is the white dwarf. The transformation is complete. But what happened to all that ejected material? It did not disappear. It forms an expanding shell of gas surrounding the newly revealed white dwarf. Initially, this shell is invisible, just hot gas spreading outward through space. But the exposed core is extraordinarily hot, with a surface temperature that might be 100,000 degrees Celsius or even higher. This intensely hot core floods space with ultraviolet radiation. When this radiation strikes the expanding shell of ejected gas, it ionizes the atoms there and causes them to glow. The shell lights up in brilliant colors, creating a planetary nebula. The planetary nebula is essentially the discarded outer layers of the red giant, illuminated by the ultraviolet light from the hot core at the center. The white dwarf that emerges from this process has several defining characteristics that make it one of the strangest objects in the universe. First, its size. The white dwarf has a radius of approximately 7,000 kilometers, comparable to Earth's radius of about 6,400 kilometers. To visualize this, imagine replacing the Sun with an object only slightly larger than Earth. The Sun's current radius is about 700,000 kilometers. So the white dwarf is roughly 100 times smaller in radius. Second, its mass. Despite being Earth-sized, the white dwarf contains approximately half the Sun's original mass. The Sun currently has a mass of about 2 times 10 to the power of 30 kilograms. The white dwarf will have a mass of roughly 1 times 10 to the power of 30 kilograms. All of this mass is packed into a sphere the size of Earth. This leads to the third characteristic: extraordinary density. The density of the white dwarf is approximately 1 million times the density of water. 1 cubic centimeter, a volume about the size of a sugar cube, would have a mass of about 1 million grams, or 1 metric ton. A teaspoon of white dwarf material would weigh roughly 5 tons if you could somehow bring it to Earth. To understand how matter can be compressed to such extreme densities, we need to understand the internal structure of the white dwarf. In ordinary matter, atoms consist of nuclei surrounded by electron clouds, with vast amounts of empty space in between. If an atom were the size of a football stadium, the nucleus would be like a marble at the center, and the electrons would be tiny specks orbiting in the stands. Most of the volume is empty space. In a white dwarf, the pressure is so immense that this structure breaks down. The electron clouds are stripped away from the nuclei. The matter becomes a plasma where positively charged carbon and oxygen nuclei swim in a dense sea of electrons. The nuclei and electrons are packed together far more tightly than in ordinary matter, filling what was previously empty space. The electrons are compressed so tightly that they are forced into a degenerate state. Every available Lanergy quantum state is filled with an electron, and additional electrons must occupy higher energy states. The electrons resist being compressed further, not because of heat or electromagnetic forces, but because quantum mechanics forbids putting 2 electrons into the same quantum state. This electron degeneracy pressure is what supports the white dwarf against gravitational collapse. Unlike a normal star, which must continuously generate energy through fusion to maintain thermal pressure against gravity, the white dwarf needs no energy source. The quantum mechanical properties of electrons provide permanent support. The white dwarf can exist in equilibrium indefinitely, balanced between gravity pulling inward and degeneracy pressure pushing outward. There is a crucial limit to this process, discovered by the astrophysicist Subrahmanyan Chandrasekhar in the 1930s. The Chandrasekhar limit states that electron degeneracy pressure can only support a white dwarf up to a maximum mass of about 1.4 times the mass of the Sun. If a white dwarf exceeds this mass, electron degeneracy pressure is insufficient to resist gravity, and the white dwarf will collapse. For white dwarfs below the Chandrasekhar limit, like the one the Sun will become, degeneracy pressure is sufficient. The white dwarf is stable and can exist forever, or at least 4 timescales comparable to the age of the universe and far beyond. Now, what will the Sun actually look like as a white dwarf? Let us paint a detailed picture of this future state. When the white dwarf first emerges from the planetary nebula, it is one of the hottest objects in the universe. Its surface temperature might be 100,000 degrees Celsius, possibly reaching 150,000 or even 200,000 degrees. At these temperatures, the white dwarf emits most of its radiation in the ultraviolet part of the electromagnetic spectrum, which is invisible to human eyes. However, it also emits substantial amounts of visible light, particularly at the blue and violet end of the spectrum. If you could see the white dwarf with your eyes, protected appropriately from the intense radiation, it would appear as an intensely bright blue-white point of light, dazzling and pure in color. It would be far bluer than any star visible in our current night sky, bluer even than the hottest massive blue giant stars. Despite its small size, the surface brightness would be extraordinary. The surface temperature is so high that each square meter of the white dwarf's surface emits far more light than the same area on the Sun's current surface. However, the total luminosity, the total amount of light emitted, would be less than the Sun's current luminosity because the white dwarf has so much less surface area. The Sun currently has a surface area of about 6 times 10 to the power of 18 square meters. The white dwarf will have a surface area of about 6 times 10 to the power of 14 square meters, roughly 10,000 times smaller. Even though each square meter is much brighter, the total light output is reduced because there are so many fewer square meters. A newly formed white dwarf might have a luminosity about 1% of the current Sun's luminosity, though this varies depending on the exact temperature and size. It would be far less luminous than the Sun is now, but still comparable to many of the fainter stars visible in the night sky. The white dwarf has no atmosphere in the conventional sense. The intense gravity at the surface, about 100,000 to 1 million times Earth's surface gravity, prevents any normal atmosphere from existing. Any gas would be pulled down to the surface and compressed into the degenerate matter. The surface is simply the boundary where the dense interior meets the vacuum of space. The composition of the surface depends on what elements have settled there. In general, heavier elements sink toward the center due to gravity, while lighter elements float to the top. Many white dwarfs have surfaces composed primarily of hydrogen or helium, even though their interiors are carbon and oxygen. These light elements were the last material from the original star to settle onto the white dwarf's surface. However, the Sun's white dwarf might have a surface enriched with heavier elements, including carbon and oxygen, depending on exactly how the envelope was ejected and whether any mixing occurred. The exact surface composition is difficult to predict, but it will be observable through spectroscopy. By analyzing the wavelengths of light the white dwarf emits, The white dwarf rotates, though probably slowly. The Sun currently rotates once every 25 days or so at its equator. As the Sun contracts to form a white dwarf, conservation of angular momentum should cause it to spin faster, much like a figure skater spins faster when pulling in their arms. However, the Sun will lose angular momentum through its magnetic field and stellar wind during the red giant phase. So, the white dwarf might not rotate as fast as conservation of angular momentum alone would predict. It might rotate once every few hours to once every few days. The white dwarf may have a magnetic field, possibly quite strong. Some white dwarfs have magnetic fields millions of times stronger than Earth's magnetic field. These fields can affect the structure of matter near the surface and influence how the white dwarf interacts with any surrounding material. As time passes, the white dwarf cools. It radiates energy into space continuously, and because it generates no new energy through fusion or any other process, it must cool down. But this cooling is extraordinarily slow. After 10 million years, the surface temperature might drop from 200,000 degrees to 100,000 degrees. The color would shift slightly from intensely blue-white to slightly less intensely blue-white, but the change would be subtle. After 100 million years, the temperature might be around 50,000 degrees. The white dwarf would still be blue-white, still far hotter than the Sun is today. After 1 billion years, the temperature might be around 20,000 degrees. The color would begin to shift toward pure white, no longer quite as blue. After 5 billion years, about the amount of time from now until the Sun becomes a white dwarf, the white dwarf might have a temperature around 10,000 to 15,000 degrees. It would appear white or slightly white, similar to bright stars like Sirius or Vega, after 10 billion years. The temperature might drop to around 5,000 to 7,000 degrees, giving it a yellowish-white color similar to the Sun's current color but far fainter due to the small size. The cooling continues indefinitely, but the timescales become enormous. After 100 billion years, the white dwarf might have cooled to around 2,000 to 3,000 degrees, glowing with a dull red color. After 1 trillion years, it might be just a few hundred degrees above absolute zero, barely emitting any light at all. As the white dwarf cools, its interior undergoes a remarkable transformation. At high temperatures, the carbon and oxygen nuclei in the interior move around relatively freely within the sea of degenerate electrons. But as the temperature drops, the nuclei lose kinetic energy and begin to settle into ordered arrangements. The white dwarf begins to crystallize from the inside out. The carbon and oxygen nuclei arrange themselves into a crystal lattice, forming what is essentially a gigantic cosmic diamond or graphite crystal, depending on the exact structure. This crystallization releases latent heat, the same phenomenon that occurs when water releases heat as it freezes into ice. This additional heat source slightly delays the cooling, but the effect is relatively minor on the overall timescale. Eventually, the entire white dwarf interior becomes a crystallized sphere of carbon and oxygen, surrounded by a thin outer layer that remains liquid or gaseous. This crystallized white dwarf continues to cool, eventually becoming a black dwarf, a cold, dark, crystallized sphere that emits no light and simply exists, supported by electron degeneracy pressure. However, no white dwarf has yet cooled to the black dwarf stage. The universe is only about 13.8 billion years old, which is not nearly enough time for even the oldest white dwarfs to cool completely. It will take at least 10 trillion years for a white dwarf to become a black dwarf, and possibly much longer. By that time, the universe will be unimaginably different, cold and dark, with most stars burned out and gone for the foreseeable future, meaning the next many billions of years. The white dwarf that was once the Sun will be visible, shining with residual heat from its formation. It will be a small, faint object compared to the Sun today, but it will still emit light, a slowly fading testament to the star that once was. If any observers exist in the distant future to look at this white dwarf, perhaps beings from another star system passing through the remnants of our solar system, what would they see? They would see a faint blue-white or white star, unremarkable in most ways, indistinguishable at first glance from millions of other white dwarfs scattered throughout the galaxy. But if they looked more closely, if they analyzed the light from this particular white dwarf, they might detect subtle signatures in its spectrum that tell a story. They might see traces of elements that hint at the composition of the original star. They might measure its mass and size and calculate its density, marveling at matter compressed to such extreme states. If they looked at the space surrounding the white dwarf, they might see traces of the planetary nebula, now vastly expanded and faded, but perhaps still detectable as a faint shell of enriched gas. They might detect planets orbiting the white dwarf, frozen worlds that once basked in the light of a yellow star, but now receive almost no warmth from the faint remnant at the center of their system. They might piece together the story of this system, realizing that this white dwarf was once a star like the Sun, that it once had a family of planets, that at least one of those planets was home to life, perhaps even to a civilization that looked up at their star and wondered about its fate, just as we do now. The formation of a white dwarf is ultimately a story of transformation and compression, of a star shedding its outer layers and revealing its dense, degenerate core. It is a story of quantum mechanics, where the strange rules that govern the behavior of electrons at the atomic scale become the dominant force, supporting a stellar remnant with half the mass of the Sun. What our Sun will look like as a white dwarf is both simple and profound. It will be small, Earth-sized, but incredibly dense. It will be hot, blazingly hot at first, cooling only gradually over billions and trillions of years. It will be stable, supported by quantum pressure, needing no fuel, no fusion, no ongoing energy generation. It will simply exist, a monument to the star that came before, a repository of carbon and oxygen created through billions of years of nuclear fusion, slowly cooling and fading as the universe ages around it. This is how a white dwarf forms. Through the progressive stripping away of a red giant's envelope until only the degenerate core remains. And this is what our sun will look like as one, a small, dense, hot, slowly cooling sphere of carbon and oxygen, shining with residual heat, a final stable form that will endure 4 time scales that dwarf the sun's own lifetime, a quiet ending to the story of the star that gave us life. When the sun becomes a white dwarf, the solar system will be transformed into something barely recognizable. A dark and frozen realm where the familiar order of planets has been disrupted, where some worlds have been destroyed entirely, and where those that remain orbit a faint, dying ember that provides almost no light or warmth. To understand what happens to the planets and asteroids after this transformation, we need to trace their fates through each stage of the sun's evolution and examine how they will exist in the strange new solar system that emerges. Let us begin with what we know about the current solar system and how it will change during the sun's red giant phase. Because the fate of each object during that tumultuous period determines whether it will even exist to orbit the white dwarf. Mercury, the innermost planet, orbits at an average distance of about 58 million kilometers from the Sun. When the Sun becomes a red giant and expands to perhaps 100 million to 200 million kilometers in radius, Mercury will certainly be engulfed. There is no scenario in which Mercury survives. As the Sun's outer layers reach and then surpass Mercury's orbit, the planet will experience increasing drag as it plows through the progressively denser solar material. This drag will slow Mercury in its orbit, causing it to spiral inward toward the denser regions of the Sun's interior. As it descends, the temperature will rise dramatically. Mercury's surface will melt, then vaporize. The planet will begin to disintegrate, leaving a trail of vaporized rock and metal in its wake. Eventually, Mercury will be completely destroyed, its atoms mixed into the Sun's outer envelope, and later ejected as part of the planetary nebula. By the time the Sun becomes a white dwarf, there will be no Mercury. The planet will have ceased to exist as a distinct object. Its constituent atoms will be scattered into space, perhaps eventually becoming part of new stars and planets billions of years in the future. Venus faces a similar fate, orbiting at about 108 million kilometers from the Sun. Venus is closer to the boundary of potential survival, but most models suggest it too will be consumed. The Sun's expansion will reach Venus's orbit, and the planet will experience the same process of atmospheric drag, orbital decay, and eventual vaporization that destroys Mercury. Yet, even in optimistic scenarios where the Sun's expansion is somewhat limited, Venus is so close that it will likely be engulfed. By the time the Sun becomes a white dwarf, Venus will probably have been destroyed, its atoms scattered and lost. Earth's fate, as we have discussed, is uncertain. It orbits at 150 million kilometers from the Sun, right at the edge of where the Sun might expand to. Whether Earth survives depends on the exact extent of the Sun's expansion, the rate of solar mass loss, and the balance between orbital expansion due to that mass loss and orbital decay due to tidal effects and atmospheric drag. The most likely scenario, based on current models, is that Earth will be consumed. The Sun will expand far enough to engulf Earth's orbit, and even if Earth initially moves outward as the Sun loses mass, the drag from passing through the Sun's outer envelope will cause Earth to spiral inward to its destruction. However, there is a possibility, perhaps a 20 to 30% chance, based on the range of different scientific models, that Earth survives if the Sun loses mass rapidly enough and does not expand quite as far as the most extreme predictions suggest. Earth might end up in a more distant orbit, perhaps at 1.5 or 2 times its current distance, just beyond the maximum extent of the red giant Sun. If Earth does survive to orbit the white dwarf, it will have been transformed beyond recognition. The intense heat during the red giant phase will have boiled away any remaining oceans and atmosphere. The surface will have melted into an ocean of liquid rock. Over time, as the white dwarf cools and provides almost no heat, this molten surface will solidify again, forming a barren, airless ball of rock. This remnant Earth will be completely lifeless. Every trace of the biosphere that flourished for billions of years will have been erased. Every mountain, every ocean basin, every fossil, every remnant of human civilization, if any still existed, will have been melted and homogenized. The surviving Earth will be a dead world, geologically inactive, frozen in eternal darkness, orbiting a faint white dwarf that provides virtually no warmth. The Moon, if Earth survives, will continue to orbit Earth. It too will have been scorched during the red giant phase. Its surface heated to the point where some volatiles might have been driven off, but the Moon is already essentially airless and geologically dead, so its appearance might not change as dramatically as Earth's. It will be a dark, frozen companion to a dark, frozen Earth. Mars has a much better chance of survival than Earth, orbiting at about 228 million kilometers from the Sun. Mars is far enough out that most models predict it will not be engulfed by the expanding Sun, as the Sun loses mass during its red giant phase. Mars's orbit will expand outward, carrying it to a safer distance. However, survival does not mean Mars will be unchanged. During the red giant phase, the intense radiation from the bloated Sun will heat Mars significantly. Any ice in the polar caps or buried in the soil will melt and vaporize. For a brief time, Mars might actually have liquid water on its surface, perhaps even a temporary thick atmosphere as carbon dioxide sublimates from the polar ice and water vapor is released from the ground. But this warmth will be temporary and will come at a cost. The intense solar wind from the red giant will strip away Mars's atmosphere, carrying it off into space. Whatever water is released will be broken down by ultraviolet radiation, and the light hydrogen will escape Mars's weak gravity. By the time the Sun becomes a white dwarf, Mars will be thoroughly desiccated, completely dry, and essentially airless. Mars will then orbit the white dwarf as a frozen, dead world. With almost no heat from the faint white dwarf, surface temperatures will drop to perhaps 20 or 30 degrees above absolute zero, far colder than Mars is today. Any remaining thin atmosphere will freeze out onto the surface as dry ice. Mars will be a silent, dark world, its red surface perhaps visible only in the faint light of distant stars, no longer illuminated by a bright sun. The asteroid belt, located between Mars and Jupiter at distances ranging from roughly 200 million to over 400 million kilometers from the Sun, will also survive the red giant phase. These rocky and metallic bodies are far enough from the Sun to avoid being engulfed, and their small size and lack of substantial atmospheres mean they will not be dramatically affected by the increased solar radiation and wind. However, the asteroids will experience some changes. The increased heat from the red giant sun will warm them significantly. Any volatile materials, such as water, ice, or frozen carbon dioxide that some asteroids contain, will sublimate into space. The asteroids will become even drier and more depleted in light elements than they are today. Some asteroids might fragment if they contain pockets of ice or other volatiles in their interiors. The heating could cause these materials to vaporize and create internal pressure. This pressure might crack the asteroid or even split it into multiple pieces. The asteroid belt might end up with more numerous but smaller objects after the Sun's red giant phase. When the Sun becomes a white dwarf, the asteroids will continue to orbit much as they did before, though their orbits will have expanded somewhat due to solar mass loss. They will be cold, dark objects, receiving almost no heat from the white dwarf. They will be illuminated only by starlight and the faint glow of the white dwarf itself. Beyond the asteroid belt lie the gas giant planets: Jupiter, Saturn, Uranus, and Neptune. All of these planets will survive the Sun's red giant phase. They are far enough from the Sun that they will not be engulfed even in the most extreme scenarios of solar expansion. Jupiter, the largest planet in the solar system, orbits at an average distance of about 778 million kilometers from the Sun. When the Sun becomes a red giant, Jupiter will be too far away to be in any danger of engulfment. However, it will receive substantially more heat and radiation than it does today. The increased solar radiation will heat Jupiter's upper atmosphere, causing it to expand and become more active. The planet's famous storms and atmospheric bands might become more vigorous and chaotic. The heating might drive stronger convection in the atmosphere, creating faster winds and larger weather systems. However, this increased activity will be temporary. When the Sun sheds its envelope and becomes a white dwarf, the heating will stop abruptly. Jupiter's atmosphere will cool and contract. The vigorous weather systems will die down as the energy input from the Sun essentially vanishes. Jupiter will then orbit the white dwarf as a cold, dark world. Its upper atmosphere will be frigid, perhaps cold enough for some atmospheric gases to condense and form exotic clouds or even snow. The planet might still generate some internal heat from its formation and from the slow contraction and cooling of its interior, but this will be minimal. Jupiter will be a shadow of its former self, a frozen giant barely visible in the faint light of the white dwarf. Jupiter's moons, however, will experience dramatic changes. The four large Galilean moons, Io, Europa, Ganymede, and Callisto, currently receive almost no heat from the Sun. Their environments are determined primarily by Jupiter's gravitational influence and, in some cases, their own internal heat sources. Io, the volcanically active moon, kept molten by tidal heating from Jupiter, will probably continue its volcanic activity even when the Sun becomes a white dwarf. The tidal forces from Jupiter depend on Jupiter's mass and Io's orbit, neither of which will change significantly. Io might remain the most geologically active object in the post-white dwarf solar system, Europa, which is believed to have a subsurface ocean of liquid water beneath its icy shell. Currently maintains this ocean through a combination of tidal heating and residual internal heat. When the Sun becomes a red giant, Europa's ice shell will begin to melt from the outside as well. The surface might temporarily transform from a frozen wasteland to a world with liquid water on its surface. This would be one of the most remarkable transformations in the solar system. Europa, currently locked in ice, might briefly become an ocean world with vast seas covering its surface. If any life exists in Europa's subsurface ocean, this might be a period when it could expand to the surface and flourish in the sunlight. However, this phase would be temporary. When the Sun becomes a white dwarf and its energy output drops dramatically, Europa will freeze again. The surface oceans will turn back to ice. If Europa's subsurface ocean continues to exist, maintained by tidal heating from Jupiter, it will once again be locked beneath a thick ice shell, isolated from the surface and from space. Ganymede and Callisto, the other large moons of Jupiter, might also experience temporary melting during the red giant phase. But they receive less tidal heating than Europa and will likely freeze solid when the Sun becomes a white dwarf. Saturn and its moons will undergo similar changes. Saturn itself will survive the red giant phase, its orbit expanding as the Sun loses mass. Its magnificent ring system, however, might not survive unchanged. The rings are composed primarily of water ice, and the intense radiation from the red giant sun might cause some of the ring particles to sublimate or be blown away by the enhanced solar wind. The rings might become less massive or even disappear entirely. Saturn's largest moon, Titan, is currently one of the most fascinating objects in the solar system. It has a thick atmosphere composed primarily of nitrogen, with methane and ethane clouds and liquid methane and ethane lakes on its surface. Titan is incredibly cold today, with surface temperatures around -179 degrees Celsius. When the sun becomes a red giant, Titan will warm up dramatically. The increased solar radiation will heat the atmosphere and surface. The methane and ethane lakes will evaporate, creating a much thicker atmosphere. The nitrogen atmosphere will expand and become more active. Titan might even warm enough for liquid water to exist on its surface, at least temporarily. Some scientists have speculated that Titan during the Sun's red giant phase might be habitable, at least by microbial life. The combination of liquid water, organic compounds, and energy from the sun could create conditions suitable for life. Of course, this is highly speculative, and whether Titan actually becomes habitable depends on many factors, including the exact temperature, the availability of nutrients, and whether the conditions persist long enough for life to emerge. When the sun becomes a white dwarf, Titan will freeze again. The methane and ethane will condense back into lakes. The atmosphere, no longer heated by the sun, will cool and contract. Titan will return to being a cold, dark world, perhaps similar to what it is today, but possibly altered by the brief warm period it experienced. Enceladus, another moon of Saturn, currently has geysers of water vapor erupting from its south polar region, evidence of a subsurface ocean maintained by tidal heating. Like Europa, Enceladus might experience some surface melting during the red giant phase, but will likely freeze again when the sun becomes a white dwarf. Its geysers, if they depend partly on solar heating, might cease or decrease in activity. Uranus and Neptune. The ice giant planets orbiting at roughly 2.9 billion and 4.5 billion kilometers from the Sun, respectively, will also survive to orbit the white dwarf. They are so far from the Sun that they will barely notice the changes during the red giant phase. They will receive somewhat more heat and light, but the effect will be minor at such extreme distances. When the Sun becomes a white dwarf, Uranus and Neptune will be among the coldest objects in the solar system. Their atmospheres, composed of hydrogen, helium, and traces of methane and other compounds, will cool to temperatures just a few dozen degrees above absolute zero. They will be dark, frozen worlds, essentially invisible except for the faint sunlight reflected from the white dwarf. Beyond Neptune lies the Kuiper Belt, a region populated by countless icy bodies, including dwarf planets like Pluto, Eris, Makemake, and Haumea. These distant objects will be almost completely unaffected by the Sun's evolution. They are so far away that even the red giant Sun will appear as little more than a very bright star. When the Sun becomes a white dwarf, the Kuiper Belt objects will continue their slow orbits in the outer darkness. They will receive no meaningful heat from the white dwarf. They will be cold, dark, and essentially unchanged from their current state. Pluto, currently visited by the New Horizons spacecraft and revealed to be a geologically interesting world with ice mountains and nitrogen glaciers, will remain frozen and dark, orbiting a sun that has become too faint to see as more than a bright star. Even farther out, at distances of thousands or even tens of thousands of astronomical units, lies the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system. The Oort cloud is the source of long-period comets that occasionally fall inward toward the Sun. These objects are so distant that they are barely bound to the Sun gravitationally. They will notice the Sun's evolution only through the change in the Sun's mass. When the Sun loses 40 to 50% of its mass during its red giant and planetary nebula phases, the gravitational pull on Oort cloud objects will decrease. Some objects, those most weakly bound to the Sun, might be released entirely and drift off into interstellar space, no longer part of the solar system. Others will remain bound, but in larger, more distant orbits. Now, let us consider what happens to the orbits of all these surviving objects. When the Sun loses mass, the gravitational force holding planets in their orbits decreases. According to orbital mechanics, if a planet maintains roughly the same orbital speed while the Sun's mass decreases, the planet's orbital radius must increase to maintain a stable orbit. The mathematics of this are fairly straightforward. If the Sun loses, say, 40% of its mass, becoming 60% of its original mass, the orbital radius of each planet will increase by a factor of about 1.67. Mars, currently at 228 million kilometers, would end up at about 380 million kilometers. Jupiter would move from 778 million kilometers to about 1,300 million kilometers. These expanded orbits mean that the planets are more spread out, with greater distances between them. The solar system becomes larger and more diffuse. The planets also take longer to complete one orbit. Orbital period depends on both the distance from the Sun and the Sun's mass, and both have changed in ways that increase the orbital period. Mars, which currently takes about 687 days to orbit the Sun, might take over 1,500 days to complete one orbit of the white dwarf. Jupiter's orbital period might increase from about 12 years to over 20 years. The outer planets would have even longer years. The dynamics of the solar system will change in other subtle ways as well. The gravitational interactions between planets depend on their masses and distances. With the planets now in different orbits than before, their mutual gravitational influences will be slightly different. Over millions of years, these small changes might cause the orbits to evolve in new ways, potentially making some orbits less stable than they were. There is a small possibility that one or more planets might be ejected from the solar system entirely during or after the Sun's red giant phase. Gravitational interactions between planets amplified by the changing solar mass and orbits might in some scenarios perturb a planet's orbit enough to send it into interstellar space. However, this is considered unlikely for most planets. The system will probably remain largely intact, with most planets continuing to orbit the white dwarf. One fascinating aspect of white dwarf planetary systems is what happens to asteroids and other small bodies that venture too close to the white dwarf. While planets orbit at safe distances, asteroids can have eccentric orbits that might bring them close to the white dwarf. The white dwarf, despite being small, has incredibly strong surface gravity, about 100,000 to 1 million times Earth's surface gravity. If an asteroid passes very close to the white dwarf, it can be torn apart by tidal forces. The difference in gravitational pull between the near side and far side of the asteroid. This creates a debris field that can spiral into the white dwarf. As this debris falls onto the white dwarf, it forms an accretion disk, a flattened ring of material orbiting the white dwarf and gradually spiraling inward. The material in the disk heats up due to friction and compression, and it can emit detectable light and other radiation. Astronomers have observed many white dwarfs with such accretion disks, clear evidence that they are actively consuming asteroids or other small bodies. Eventually, the material from the accretion disk falls onto the surface of the white dwarf. Because the white dwarf has such strong gravity, material falling onto its surface releases tremendous amounts of energy. The infalling debris can create bright spots on the white dwarf surface and temporarily increase its luminosity. Over time, this process deposits heavy elements onto the white dwarf's surface. Normally, heavy elements should sink into the interior of a white dwarf due to gravity, leaving only the lightest elements at the surface. But if a white dwarf is actively accreting material from disrupted asteroids, its surface can become enriched with elements like iron, magnesium, silicon, calcium, and others. Indeed, observations of many white dwarfs show exactly this signature. Their spectra revealed the presence of heavy elements that should not be there if the white dwarf had been left undisturbed. This is strong evidence that white dwarfs are actively consuming asteroids and planetary debris, a process called white dwarf pollution. This means that the asteroid belt in the post-Sun solar system might not be stable forever. Over millions or billions of years, gravitational perturbations might send some asteroids into orbits that pass close to the white dwarf. These asteroids would be disrupted and consumed, their atoms raining down onto the white dwarf's surface. In this way, the white dwarf sun would, in a sense, be eating the remnants of the solar system. The rocky material that once formed planets and asteroids, material that includes elements created in previous generations of stars and brought together in the solar nebula for 0.6 billion years ago, would be falling back onto the remnant of the star that once illuminated this system. There is also the possibility of planets orbiting very close to the white dwarf, closer than any planet currently orbits the Sun. During the red giant phase, planets might spiral inward due to drag, but if they survive without being completely destroyed, they could end up in tight orbits around the white dwarf. Some white dwarfs have been discovered with planets orbiting at distances of only a few 100,000 to a few million kilometers, far closer than Mercury orbits the current Sun. These planets somehow survived the red giant phase, perhaps because they were originally farther out and migrated inward, or perhaps because they formed from debris after the white dwarf formed. These close-orbiting planets would be tidally locked to the white dwarf, always showing the same face, just as the Moon is tidally locked to Earth. One side would perpetually face the white dwarf and be slightly warmer, though still extremely cold by any reasonable standard. The other side would face away into eternal darkness, cooled only by the faint light of distant stars. The question of whether planets can survive the red giant phase and end up in close orbits around white dwarfs is an active area of research. Observations suggest it is possible, and some white dwarfs definitely have planetary companions. Whether the Sun's white dwarf will have such companions depends on the details of how the solar system evolves during the red giant phase. What would it be like to stand on one of these surviving worlds orbiting the white dwarf that was once the Sun? Let us imagine standing on Mars billions of years in the future after the Sun has become a white dwarf. The landscape would be familiar in some ways. The rust-colored rocks and dusty regolith would still be there, shaped by billions of years of geological history, but the sky would be utterly alien. During the day, if you can call it day, the white dwarf would be visible as a brilliant blue-white point of light, far brighter than any star, but incomparably fainter than the Sun appears from Mars today. The white dwarf would subtend a tiny angle in the sky, even though it is closer to Mars than the current Sun is. Due to Mars's expanded orbit, the white dwarf is so small that it would appear as a point, not as a disk. It would be like looking at an extremely bright star, not like looking at the Sun. The amount of light and heat from the white dwarf would be negligible. The surface of Mars would be frozen to temperatures approaching absolute zero. Any thin atmosphere that remained would have frozen out onto the surface long ago. The landscape would be illuminated primarily by starlight, with the white dwarf contributing some additional light but not enough to make the scene appreciably brighter than a moonlit night on Earth. Looking up, you would see the stars undimmed by any atmosphere, since Mars's atmosphere would be gone. The constellations would be largely the same as they are today, since even billions of years is not enough time for stellar motions to significantly rearrange the nearby stars. The Milky Way would stretch across the sky, a river of stars utterly magnificent in the airless dark. Jupiter, if it were in the right part of its orbit, might be visible as a faint point of light, reflecting a tiny amount of light from the white dwarf. Saturn, Uranus, and Neptune would be too faint to see without a telescope. Earth, if it survived, would be invisible. Lost in the glare of the white dwarf when on the same side, and too faint to see when opposite. It would be a scene of profound desolation and beauty, a dead world orbiting a dying star illuminated by the light of the galaxy, silent and still, waiting for nothing in particular as trillions of years pass and the white dwarf slowly fades to black. This is what happens to the planets and asteroids after the Sun becomes a white dwarf. Some are destroyed, consumed by the red giant Sun. Others survive, but are transformed by heat and radiation and then frozen in the darkness when the white dwarf emerges. They orbit in expanded trajectories, spread farther apart, moving slowly through the void around a faint remnant of the star that once gave them light. Some asteroids might be disrupted and consumed by the white dwarf. Some worlds might end up in close orbits. But overall, the solar system becomes a graveyard, a collection of frozen dark worlds, monuments to a planetary system that once thrived under a bright yellow star, now reduced to faint echoes orbiting a slowly cooling ember that will shine for trillions of years before finally fading into eternal darkness. The question of how long a white dwarf lasts and what happens when it finally reaches the end of its existence touches on timescales so vast that they challenge our ability to comprehend them. To understand the answer, we need to explore the nature of white dwarfs, the physics that governs their cooling, and the ultimate fate that awaits them in a universe far older than anything we can currently observe. A white dwarf is, in essence, a stellar ember. It is not generating energy through nuclear fusion or any other active process. It is simply a hot, dense sphere of matter, primarily carbon and oxygen, in the case of white dwarfs formed from stars like the Sun, slowly radiating away the residual thermal energy from its formation. The white dwarf is cooling, and the question of how long it lasts is really a question of how long it takes to cool completely. When a white dwarf first emerges from the planetary nebula that surrounds it, it is extraordinarily hot. Surface temperatures can reach 100,000 degrees Celsius or even higher, sometimes approaching 200,000 degrees. The interior is even hotter, potentially reaching tens of millions of degrees. This heat is the legacy of the star's former life, the accumulated thermal energy from billions of years of nuclear fusion and gravitational contraction. From the moment of its formation, the white dwarf begins to cool. Photons carry energy away from the surface, radiating into the vacuum of space. The surface temperature gradually decreases, and heat from the interior conducts outward to replace what is radiated away. This is a one-way process. The white dwarf has no mechanism to generate new heat, so it can only cool down, never warm up. However, the cooling process is extraordinarily slow. This is because white dwarfs have enormous heat capacity, despite being only about the size of Earth. A white dwarf contains roughly half the mass of the Sun, all compressed to incredible densities. There is simply an enormous amount of thermal energy stored in this compact object, and it takes a very long time for all of that energy to radiate away. To understand how slowly white dwarfs cool, we need to understand the physics of heat transfer in these extreme objects. Heat moves from the interior to the surface, primarily through conduction. The interior is filled with degenerate matter, a plasma of carbon and oxygen nuclei swimming in a sea of degenerate electrons. The electrons, despite being in a quantum mechanically constrained state due to degeneracy, are still able to carry heat through the material.